Hello, Jaka sir. How is your university going in your leadership?
Professor Mishra?
Yeah.
Yes, fine, going on. Today's holiday, but I have another meeting at 1 o'clock.
Oh, good. No problem. Professor Helen Kanta will replace you, sir. No problem.
No, there is no problem online.
Yeah.
We should start, Professor
Yeah.
Mishra.
Yes, with your permission, Amit will start. Yeah, it is done. Yeah.
Sir, should we start?
Yeah, with the permission of chair, you should start.
Okay.
Okay, PM Mishra, you have to tell something, or I should start?
Yeah. Amritji, please.
Okay.
Introduce your guest.
Sir, am I audible?
Yeah, you are audible.
Okay. Good morning, good afternoon, and good evening to all of you wherever you are. Greetings from Association of Chemistry Teachers, here of Homi Bhabha Center for Science Education, EIFR, Mumbai, India. Today we are on the third day of the National Convention of Chemistry Teachers, NCCT 2020, and the International WebCon on recent advances in chemistry education and chemical research. We have already successfully completed 2 days of NCCT, and for the past 2 days, we have got the opportunity to listen to many speakers across the globe. We have learned so many things from them. Thank you, respected dignitaries, for enriching all of us in your special way. All these speakers of this web conference have such illustrious lists of achievements that if we talk about their achievements alone, the entire duration of the WebCon will be covered, but the list may not end. We have always known them to be extremely helpful to our students and dedicated to the service of education. They have always supported the chemistry fraternity with their unquestionable sincerity and commitment. Today we have with us Professor D.V. Prabhu sir, General Secretary ACT, Professor B. Pare sir, President ACT, Professor P.M. Mishra sir, Vice President ACT East Zone, and the convener of the NCCT 2020, and all ACT members. We also have Dr. Venkat Narayan, Principal Polymer Consultant, Anthera Technologies Consulting, Texas, USA, Professor Shurabh Pal, Director, IISER Kolkata, Professor S. Sivaram, INSA Senior Scientist, IISER Pune, Professor P. Ramasamy, University of Mauritius, Professor Andy Gravett, University of Brighton, UK, as keynote speakers, and Professor Nageshwar Rao, Vice Chancellor, IGNOU, New Delhi, as chief guest, and as a guest of honor, Professor Dolly Sinha, the Pro Vice Chancellor of LNMU Darbhanga. A warm welcome to all of you, respected dignitaries, ACT members, faculty members of various institutions, and dear students. May I now request Professor D.C. Deka, Vice Chancellor, Madhav Dev University, Assam, and ex-president of ACT, chair the session. With the kind permission of the chair, I now want to welcome Dr. Venkat Narayan sir. He is the Principal Polymer Consultant, Anthera Technologies Consulting, Texas, USA. Venkat Narayan sir, he completed his PhD in chemistry from Virginia Tech, USA, and his thesis topic was Synthesis and Characterization of Processable Aromatic Polyamide Imides. Sir completed his MSc MTech in Plastic Technology from University of Bombay, India. Sir also completed his BSc from University of Bombay. Sir is having 12 patents and 15 invention disclosures. Sir is the technical executive with extensive experience in research and development, demonstrated track record of achieving stability, growth, and new materials development, demonstrated leadership and successful team building capabilities, sound technical communication, presentation, and personal development skills. That is experienced in characterizing and transforming materials developed in the laboratory to commercial products. He is involved in the regulatory discussion with FDA US, BSI Europe, and PMDA Japan for device approvals. Out of several key accomplishments, he developed and validated an oxidatively stable orthopedic device for commercial launch in June 2009. He developed and implemented a wholly water-soluble UV blocking formulation for spectacle lenses in January 2005. He launched tintable and tinted lens produced in a range of ophthalmic materials in August 2004. He provided expertise on polymer science and plastic technology for materials for medical device, aerospace, industrial, and consumer applications. May I now welcome sir to please take over.
Thank you, Dr. Amrit. Namaskar to all of you. It's my pleasure to share the final day technical session in this web conference organized by National Convention of Chemistry Teachers. I thank convener Professor P.M. Mishra and our General Secretary Dr. D.V. Prabhu for giving me this opportunity to share this technical session. In this technical session, halfway, I will share only 2 lectures. First lecture will be delivered as already introduced by Dr. Amrit Mitra. Dr. Venkatanarayan is a renowned polymer chemist. And second lecture by Professor Saurabh Pal, he is a renowned organic chemist. And as Venkatanarayan has already been introduced, we will be delighted to hear him. I now request the first speaker, Dr. Venkatanarayan, to present his lectures. Welcome, Dr. Venkatanarayan.
Thank you, Professor Dekaf. And thank you, Dr. Mitra, for your kind introduction. It's a pleasure and a privilege for me to participate in the National Convention of Chemistry Teachers 2020. And it's an honor to be able to present in this August forum. My topic is advances in polymer blends. My background is in polymer chemistry, and so I thought that this would be an appropriate topic to cover today with the audience today. Okay, why is it not moving? Okay. So just to give a brief introduction, most of you are already familiar, but for those who are not in this field, polymers are organic macromolecules with very unique properties that have found application in a wide variety of fields. This is because there are many hundreds of thousands of different polymers, and each has got their own set of physical, chemical, mechanical, and other properties like optical and electrical. So as a result, you can think of a wide range of applications into which these materials can be applied. As I said, these include consumer products, aerospace, construction, engineering, and healthcare. And the reason is that polymers are very versatile materials. So they can be customized in order to fit into an application. So if there is an unmet need, then one can think of a polymer with the appropriate properties that can be used to fulfill that need. Just a very generic overview, you can see that pictorially, I am trying to show that there is a wide variety of applications into which polymers can be used, right from windshield glasses to boats to even very high technology radar transparent stealth aeroplanes. Apart from that, it's used a lot in electronics, in printed circuit boards, in clothing, in mechanical applications, protective helmets, and so on. And of course, one of the most important areas in which these materials are applied today is in the area of healthcare. And I'll be talking a little bit of that. Just again, I apologize if some of this is very basic, but I just thought it would be relevant to give a brief background into some of these materials.
ability of the photoanode in visible range is also increasing. This is
I'm sorry. Is it okay to continue?
Okay, fine, please.
Yeah. So so as we know that conventional organic molecules, we are familiar with a lot of the small molecules with molecular weight no greater than about 200, 300, maybe even up to 1,000, and they are much smaller than the macromolecules or polymer molecules, which could have a molecular weight in the range of tens of thousands. So here you see that if you have a simple moiety like this, we can call it a monomer if it's got reactive groups R1, R2, R3, and R4. And when they are reacted, it can form a long chain and thereby create a very large molecule. And basically, this large molecule consists of a repeat unit which repeats itself n number of times. And the n is typically in tens of thousands. So the molecular weight we are talking of could be in hundreds of thousands and in some cases even in millions. These are the polymer molecules. What are the features of these molecules? The most obvious one is that it's got a very high molecular weight. These polymers are all synthesized using basically the same conventional chemistry that we are all familiar with, but there are some specific conditions. All reactive molecules must have a minimum functional reactivity of 2 groups per reactant. So each reacting molecule will have at least 2 groups that are reacting. If it does not have 2 groups, then the chain will stop after one is reacted because it cannot propagate at the other end. And polymerization reactions are also driven by unidirectional and predominantly irreversible kinetics. So the direction of the polymer is always in the forward direction, and the propensity for a reverse reaction is minimized by either by the nature of the chemistry used or by certain conditions whereby you prevent the reverse reaction from taking place. And the most key functionality that is necessary for the success in polymerizing a high molecular weight is reaction stoichiometry. The stoichiometry is important in the sense that if you have 2 molecules, each with a functionality of 2, you want to make sure that the stoichiometric ratio between the 2 reacting materials is exactly 1 or very close to 1. The closer it is to 1, as the ratio tends to come closer to 1, the molecular weight tends to go higher. And there are whole books written on how this stoichiometric ratio can be leveraged to make a wide range of molecular weights. Now, in the case of the polymerization reaction, the synthesis can occur through largely one of 2 broad mechanisms. The first one is the step growth. These are typically also called condensation polymers. And these include things like polyesters, polyamides, polyaryl ether ketones, and sulfones, and so on. The other mechanism by which the reactions can occur is through a chain propagation reaction, typically activated through either thermally or through a free radical or ion-initiated polymerization. And polymers of this class are the polyethylenes, polyalkenes, acrylates, methacrylates, ring-opened polymers such as polyalkylene glycols, siloxanes, certain polylactones, and so on. And these are all done by a kind of a chain growth mechanism. Now, let's look at some of the, let me see if I can hide this. This is so that the title is, there we go. So let's look at some examples of materials. Okay. So these are some typical examples. As you can see, what I've shown here is a polymer, not in its entire chain, but taking a basic unit that gets repeated over and over again. So you can think of polyethylene. So you have an ethylene moiety that repeats itself n times. Acrylates and methacrylates. So here you have an acrylic functionality that is repeated n number of times. Or a siloxane, nylon, where you have a polyamide. So you have an amide linkage that repeats itself. Similarly, you can have polyurethanes, polyaryl ether ketones, or polyesters. These are basic examples. So you can see that the common pattern in all of these materials is there is a basic repeat unit which has a small molecular weight, but it is repeated thousands of times to give you your large molecular weight. Now let's look at copolymers. Copolymers are nothing but an extension of conventional polymers of the type we just saw, like the polyesters and polyamides and polyether ketones. However, now the same chain can contain more than one type of repeat unit. So instead of having just all polyamide units repeating themselves, or polyester units repeating themselves, or an ethylene unit repeating itself, now you can consider polymers containing two types of repeat units. So you have an amide. So for example, you could be talking of, let us say, a polymer that has both an ester linkage as well as an amide linkage, and both of them are independently present in a number of times. And so such polymers that contain more than one type of repeat unit functionality are called copolymers. And these copolymers, for example, there are copolymers that are commercially used containing polyester and polyamide linkage, and these are now referred to as polyester coamides or amides. So therefore, it has got both these functionalities. Another example is very well known to us as synthetic rubbers, like styrene butadiene or styrene acrylonitrile or nitrile rubbers. So these are all examples where you have combined two different growing chains of repeat units in the same molecule. And when we talk about this, the natural question is, why copolymers? What is so unique about them? The main thing is that we know that polymers are very versatile, like I showed in my earlier slide, that polymers are used in a wide variety of applications. So polymers by themselves are extremely versatile. However, copolymers are a material designer's dream come true, because now you can actually attack complex problems with one material. So instead of using multiple materials to solve multiple problems, you try to find a single material that can solve multiple problems. So therefore, you look for, excuse me, a material that can have characteristics of a diverse nature. Some examples of these are, for example, rubber toughened epoxies. Now here you have the rubbers that are chemically bonded to epoxy units. As you know, epoxies are very, very strong adhesives. They are very strong materials with very high tensile strengths. However, because they are very strong, they have a problem that they are very brittle. So they can be strong, but they can be very brittle. So in order to help a load-bearing material that is using epoxy to also have toughness, what we do is we incorporate a rubber or a flexible molecule into the chain. And when we do that, the rubber acts as a impact modifier. It acts as a toughener for the epoxy. So now the composite material has both strength and toughness. And that's the versatility that you have introduced by having multiple materials in the same molecule. Another example is a very classic one, which is the contact lenses, extended wear contact lenses that we wear, a lot of people wear today. And they are nothing but silicone hydrogels. And I'll be talking a little bit more of the structure a little later on. But what it does is it combines the hydrophilic properties of a polar molecule that is present in acrylates, along with the very extremely hydrophobic silicone molecule. So the same same unit or the same molecule has both hydrophilic as well as hydrophobic groups. And these have a number of applications, but this is one example where it is used, and that's in extended wear contact lenses. And we will talk about some of the other copolymers that have, where you have hydrophilic and hydrophobic groups, and where they have got a number of uses. So let's talk about the different types of copolymers. Copolymers can be classified into 4 different types of materials. The first is called a random copolymer. So as I said, you have 2 repeat unit types. Now here you can see that let's say if A is a repeat unit type 1 and B is a repeat unit type 2, what you have along the chain is some random distribution of these 2 repeat units. And as a result, you have a total randomized composition in the overall polymer chain, and these are called random copolymers. On the other hand, if you have perfectly alternating A, B, A, B, A, B, then you have now a perfectly alternating copolymer. The third type is a block copolymer. So as the name suggests, what you have is a whole block of 1 repeat unit. And once you have a significant molecular weight, you now transition into the second repeat unit in another block. So now you have blocks of 2 different materials. Now, I'll just pause here to just tell you the difference between a random copolymer and a block copolymer. In the case of a random copolymer, what you end up doing is, because it is you take both the materials or both the chemical moieties and you have randomized them into the same molecule, there is no distinct weightage of any one type of property. So you end up with homogenization of the overall properties, which are some composite combination of both types of the properties. On the other hand, in the case of block, since you have individual identity of the A type block and the B type block, you now have not a homogeneous set of properties, you have heterogeneous properties. You have actually one set of properties as well as a second set of properties. Remember I said about hydrophilic and hydrophobic in the same material, or strength and toughness in the same material. You can incorporate that using this kind of technology. And we'll look at some examples of this. And then the final one is called a graft copolymer. In the case of a graft copolymer, you have a primary chain which is of 1 moiety. So for example, here you can see along the horizontal a row of A units forming a chain. You now have the second moiety growing off of it like a branch. And when that happens, you again get some very unique properties of materials, and these are called graft copolymers, or where B is grafted onto a chain of A. So these are the different types of copolymers by way of classification. I will now go into some of the specific examples in each of these. So let's look at random copolymers. Now, one of the earlier examples is of styrene acrylonitrile copolymer, and here this is one of the first examples of a synthetic rubber that was prepared, called styrene acrylonitrile or nitrile rubber. And here you can see that you have the monomer styrene, and the styrene has got this double bond, which is the reactive functionality here, and acrylonitrile molecule here has also got a double bond. And what happens is that if you use a free radical mechanism, you can activate the homolytic fission of these double bonds, and you can create a chain reaction that propagates by attaching the free radical end to another monomer molecule and propagating the reaction. So if you have a free radical initiator, and in the presence of activation by either heat or by radiation, now you can end up with a molecule that has both styrene and acrylonitrile units in it. Now, if you look at it, here there is a styrene moiety, and you have the acrylonitrile moiety. But you can see that there is no systematic pattern of styrene molecules followed by acrylonitrile molecules. They are all randomly distributed along the chain. So this is a good example of a styrene random copolymer. Let's look at another example. This example is the one I talked about in terms of the contact lenses, where if you do a bulk or a solution polymerization of a variety of hydrophilic acrylates, such as hydroxymethyl acrylate HEMA with, say, a hydrophobic silicone, now you have an extended wear oxygen permeable lenses. So I'll just show you the different components. These are the methacrylates here. And then you have the hydrophilic methacrylate, which is the hydroxyethyl methacrylate. And you also have a hydrophobic oligomer, which is the dimethyl siloxane dimethacrylate. So here you have, this is an oligomer because it is not a full polymer, but it has got, say, a couple of thousands molecular weight. And now at the end of the chain, you have reactive groups. You have acrylic groups on either end. So when these three components are mixed and activated or initiated, through either free radical mechanism, what happens is you get a polymer chain or a polymer molecule that contains all these materials in some random, mix throughout the material. Now, what it does is, as a result, you have these groups present, this hydroxy group here, it's a dangling chain end. And these hydroxy groups, because of their polarity, will be very hydrophilic. On the other hand, you have these silicone molecules, which are hydrophobic. So you have both hydrophilic and hydrophobic properties incorporated in the same material. Now, if you take any of the leading contact lens manufacturer, they have all used the same principle to create the extended wear contact lenses. The specific nature of the methacrylates and components may be different. The composition of the mixtures may be different with company to company. But essentially, this is the principle for what are called silicone hydrogels or SiHy materials that are used as contact lenses. The hydrophilic components in the molecule are responsible for giving good wettability to the teardrop in the eye so that it can attach itself to the eye nicely. On the other hand, the silicone groups provide what's called very good permeability to gas. Silicones have the property of having very high gas permeability. So what it does is it allows for a lot of oxygen interchange between the eye and the atmosphere. And so it keeps the eye oxygenated. And that is why these lenses are called extended, where you can wear it for a long time. So this is a very good example where you've married different properties to create in the same material all the requirements for that application. Let us now move on to alternating copolymers. In the case of alternating copolymers, one of the examples is a styrene alt maleic anhydride. Here what we see is, again, you see here the styrene molecule and you have a maleic anhydride. Maleic anhydride also has a double bond. Now, the interesting thing about maleic anhydride is that maleic anhydride by itself, even though it has a double bond, does not undergo homopolymerization. So if you are just maleic anhydride, you cannot get polymaleic anhydride. And I think that part of the reason is that this group is impacted by the presence of a vicinal carbonyl groups that are polar and electron withdrawing. So what you notice is that the reactivity ratio for maleic anhydride is not favored with itself. However, it is very favored with another molecule such as styrene. So when you have styrene and this, what happens is you end up with a perfectly alternating copolymer where you have one moiety, which is the styrene moiety, and the second is the maleic anhydride moiety. They are perfectly alternating. So you have one styrene followed by a maleic anhydride, followed by a styrene, followed by a maleic anhydride. So this is a very good example of a alternating copolymer. Another example of an alternating copolymer is one that is prepared using a polymethyl methacrylate alt styrene. So here you can see again that you have a styrene moiety and a methyl methacrylate moiety that are perfectly alternating with each other along the polymer chain. And again, because of these materials now being alternating, they don't have distinct properties of the parent material, but they have a hybrid combination of properties of both materials. And that is useful in certain commercial applications. What about block copolymers? The block copolymers, the first block copolymer was a surfactant called Pluronics, and this was prepared by creating a block of propylene oxide and a block of ethylene oxide. So here is the structure. The ethylene oxide is more hydrophilic. The propylene, because of the increased alkane chain length along the molecule, is less hydrophilic. It's more hydrophobic. As a result, now you have if you have this material in it can be used as an effective surfactant, because this group would be able to compatibilize with hydrophobic molecules, while the ethylene oxide can compatibilize with the hydrophilic materials. Therefore, you can use this, for example, to create stable suspensions and emulsions between oil and water, for example. Another example is commercially available thermoplastic elastomers. Now, we talked about styrene acrylonitrile. Another example is styrene butadiene styrene, where again you have the styrene reacting with butadiene. Now, because the butadiene has got a conjugated double bond, when the reaction takes place, as most of you are already familiar, that conjugated double bonds lead to a 1,4 addition rather than a 1,2 or 3,4 addition. As a result, what you end up with is you can have a living polymerization, which is a completely different topic altogether. But what it does is, a living polymerization is that the molecule is still continuing to be active as long as there's monomer available, and it is very controlled in the polymerization. As a result of which, you can create a whole length of styrene and then add the butadiene in to form a second block of butadiene chains in the chain, and then add again the styrene in. So now what you have is you have a multi-block polymer, or it's called ABA block copolymer, where you have a styrene, butadiene, styrene, or SBS rubber. Again, these have got very useful applications, and you will note that both the double bonds do not react in this case because they are conjugated. It ends up with being a residual double bond in the molecule in the final polymer. When we come to graft copolymers, you will recall that you create a single chain of one moiety, and then you grow on the backbone of that a second polymer. And so in this case, for example, high impact polystyrene is synthesized by grafting styrene onto the backbone of the butadiene. So this is what it is. So you now have a butadiene is first polymerized to give you a polybutadiene chain. And you'll recall that I had said that there are unreacted double bonds along the chain. Now you leverage those unreacted double bonds by reacting it with styrene. And so now styrene grows off of that. And so you have these branches of polystyrene that hang off of a butadiene. Now, as a result of this, here again, just like the rubber toughened epoxies, polystyrene is a very strong material, but butadiene is a very flexible material. So within the molecule, the butadiene acts like a shock absorber. And so if, for example, if you take a polystyrene material, just a pure polystyrene, it's glassy. And so if you hit it with a hammer, it will break. But if you have it modified with this butadiene in this manner, you'll find that the energy to cause it to break will be much higher. And so this is how high impact polystyrene is created using the grafting technique. Now let us look at some advances in block copolymers. One of the examples I'm going to talk about is a polyimide siloxane block copolymer, and that's used for gas separation membranes. Now, this is the structure, and there is a reference at the bottom that tells you of the paper in which it is drawn from. So this is a polyimide block, which is capped on either end with siloxane blocks. So as a result, you have a polyimide and a siloxane block copolymer. Typically, the molar ratio is you have about 60 to 65% of the polyimide in the overall composition and about 30-35% of siloxane in the composition. As a result, what you get is you get a phase separated system. You get a micro phase separated system where the siloxane is dispersed in the matrix of an imide. The imide has got very strong properties, so you can think of very thin membranes or thin films which are very strong. But now, if you apply it for gas separation, it combines the properties of both the imides as well as the siloxanes. And how is that? Imides are very, they have a very low gas diffusion or gas permeable coefficient, but they are very selective. So, for example, if you are trying to send through, let us say, air through this membrane, it will separate the air by allowing the smaller molecule of nitrogen through first and then the larger molecule of oxygen. So you can separate them that way. However, because it is very low in its gas permeability, what happens is the rate of the separation is very low. When you have the siloxane dissolved or it's dispersed in the matrix, now siloxanes have got a very high permeability, but by virtue of which they also have very poor selectivity. So what you do is you design depending on the gases you want to separate, you can design it so that it has both a high selectivity as well as a high permeability. And so you have more efficient gas separation. So that's the principle on which this molecule was developed. Let's look at another example for block copolymers. This is a very interesting one. This is using a polyimide propylene oxide copolymer, and it's used in printed circuit boards. Now, many of us, we remember how big the computers were with the hard drives, very massive computers, about just 20 years back. Now, over time, we can now do all of that computing within our smartphone. How is that possible? It's possible because we've been able to miniaturize and make the processors smaller and smaller in size. And how have we been able to do that? We've been able to do that using some technology very similar to this. This is in fact a technology that was developed for IBM, and I'm showing you here a phase diagram of the imide propylene oxide. So here you can see the dark. This is a scanning electron micrograph here, and I think this bar here at the bottom is, I think it is 500 microns. So so you can see that it's a high magnification here. Now, if you look at this, the darker portion is the continuous phase of the polyimide. The white spheres dispersed in that is the propylene oxide. So this polymer is first prepared to create this microphase separated system. Polyimides are thermally very stable up to 450 degrees Celsius, whereas the propylene oxides will start decomposing by under 200 degrees, at about 200 degrees. So what you do is, once you prepare this film or material, you now heat it so that the propylene oxide actually decomposes or degrades into its monomer, and it is actually volatilized out. So what leaving behind in those white spaces is air. And this is very interesting because air has got the lowest, one of the lowest conductance, in various materials. Because of its low conductivity, now you have a material where you have created an increase in the resistance of the material to such an extent that if you use this material as a printed circuit board, you can put more copper lines adjacent to each other, closer to each other, without causing any crosstalk between the two lines of copper. So that is how you are able to increase the density of the signal conveying copper wires, and you can compact it into a smaller area, And that is how this whole miniaturization has been effected. So this is one of the principles that has been used to create a how you have taken the processing from a size that was as big as a desktop computer, and you have been able to actually miniaturize it into and create a circuit board that can fit into the telephone or a smartphone, and now you can do the same computing off of a smartphone. Again, it's with the use of copolymers such as this. Let's look at some recent advances in graft copolymers. I'm going to talk about the grafting of 2-methacrylyl oxyethyl phosphorylcholine, or MPC, which is grafted onto a ultra high molecular weight polyethylene, or UHMWPE. And UHMWPE, I think I've given a couple of talks, many of you have heard me, is one of the essential elements in any articulating bearing orthopedic joints in the knee and the hip. The thing is that ultra high molecular weight polyethylene, because it's polyethylene based, is very hydrophobic. So what you've done is, by grafting a very hydrophilic material like phosphochlorine onto this, you create, for example, if you can see here in this cartoon, that this base is really polyethylene block, and off which you're growing these MPC chains. So now what happens is that this MPC is now very, very, very hydrophilic. As a result, the contact angle of the material really goes down to very close to zero. It's at 10 degrees. So polyethylene has a contact angle of about 70 or 75 degrees. So it goes from 75-degree contact angle to about a 10 degree or less. So what happens is that you create a film on top of this of water that can spread itself, as a result of which now you have, just like oil between machinery parts, you now have a lubricant that acts efficiently between articulating members within the human body, whether it's in the knee or the hip. And so you're created a lubricious articulating orthopedic joint by grafting a hydrophilic material onto a hydrophobic structural material. So this is an example of a recent advance. This was actually published in the Biomaterials Research recently in 2019. I'm going to take a few minutes to talk about what are called interpenetrating networks. Once again, many of you may be already familiar with this, and so I apologize. But for those who aren't, it's a very interesting concept. What you talk about when you talk about interpenetrating network is a blend of 2 or more molecules, polymers, into into one material. Now you imagine, for example, you take a let's take water. You take water and you put some common salt in it and you stir it up. You have dissolved the salt into the water, and as a result of the solution, you now have a dispersion at the molecular level of the salt in water. In the case of polymers, there are techniques used for blending 2 polymers together, like extrusion, shear, using a rapid shear machine, and so on. But because of its high viscosity and high molecular size, physical mixing of 2 polymers very rarely results in efficient blending at a molecular level. So how do you do that? This is a good example of how you can do it, because what you do is you have 2 chains that grow independent of each other with no chemical interaction between them. They grow together into a single molecule or a single material, and that is called an interpenetrating network of 2 independent polymer chains. So in this, at least one polymer is synthesized in the presence of a second polymer. Can somebody mute? I think. Thank you. So the individual polymers may be physically entangled.
Sorry to interrupt you. So
yeah.
This is Sunny. Sorry to interrupt you. I am force muting all. In that case, you also are going to get muted. I request you to please unmute yourself.
Okay.
So now you can unmute yourself.
Can you hear me now?
Yes, sir, you're audible.
Okay, thank you. So, so in this case, the individual polymers may be physically entangled, but they do not have any chemical bonds between them. And as a result, because you have this intimate mixture at a molecular level, you have very efficient mixing. And very interesting properties are resulting from these kind of materials. For example, one of the synthesis methodologies as follows. You take one of the monomer types and you polymerize it. So you create, let us say, a network using that one. Now you add this polymer into a second monomer, which will actually swell it up, and it will be present as a, it'll act as a solvent for this polymer. But now when this is cross-linked, it forms its own network, which is shown in the dotted lines here in this cartoon. So you have these two separate networks that are, but they are existing at a molecular level with each other. Because of this, you have very interesting properties. And this is actually from a Polymer Blends handbook, which talks about different types of blends, and interpenetrating networks is one type of thing. Very interesting chemistry. Briefly, I'll just go over the applications. A good example is some of the recent low VOC latex coatings and paints that we have. So to avoid using solvents, what they do is they dissolve the polymer in a monomer rather than a solvent. So the solvent, the monomer acts as a solvent, and then as it dries, it's not by evaporation of any volatile material, but by polymerization of that liquid material, and so it dries that way. And so that's how you get the low VOC latex coatings. You can think of nonlinear optic applications where you have two completely independent set of optical properties in these materials, and as a result of which a combination gives you very good platform for nonlinear optics. And I am partial towards biomedical because that's an area I've worked for so long. And you can see that these materials have been applied in gradient refractive index contact lenses, in controlled transdermal drug delivery. So you have a very strong material which is intimately mixed with the hydrogel. Now the hydrogel can actually be a drug carrier and deliver that. And some of the recent advances in creating artificial teeth and steam sterilizing tubing or burn dressings, these are all done using the interpenetrating network technology. Similarly, you can think of two materials, one very elastic and the other highly viscous material that are intimately mixed together. The viscous material can act as an effective sound and vibration dampener, and therefore it can be very effective in that application. The last application that's interesting here is solar heating panel coatings. Now the solar heating panels will absorb or will get heated a lot by absorption of sunlight. Typically, as we all know from our basics in thermodynamics, that when you have energy absorbed, it will create a lot of energy within the molecules to create kinetic motion of the molecules. Now, what you're doing here is, because these materials, even though they have increased, and that usually what happens is if you have a mixture, they tend to agglomerate. So they tend to phase separate. But here, because the two materials are so intimately mixed that, and they're entwined in each other, entangled to such an extent that that does not happen. And so the properties are maintained even through a wide range of temperatures. And so that's another effective application for these IPNs. What is the next frontier for these copolymers? I've talked about different applications. I've talked about how different properties can be combined together. Now, the one area in the healthcare field, which is like the ultimate frontier or the horizon, is replacement for cartilage. The bone cartilage, so you have very soft cancellous bone, which is, on top of which is some subchondrial bone and cartilage, calcified cartilage, which is very hard. So you can see that here you have a very unique structure. And then you have a transition zone of material that has some structural integrity, but it starts showing more hydrophilic properties. And then the surface of the cartilage is very, very lubricious, very, very hydrophilic, and very, very soft. This is a very complex structure that cannot be made using a single polymer. But I'm just going to show you one concept that it has been is under development right now. So imagine, if we wish, that you have bone here, and you now start putting in a cartilage-like hydrated material that is built on top of this gradient, which is built on top of a bone-like stiffer anchoring surface, which can now bond to the bone. So what happens is, now you can think of either a single polymer with a copolymer with different ingredients, or you can graft one layer, then a second layer, then third layer, and so on, and you can come to this point. Now, this is only conceptual at this point, but there are some companies are made a lot of advances in this area. Unfortunately, because of my confidentiality with them, I cannot disclose either the materials or the companies, but just letting you know that this is a frontier that's being addressed to create what is called synthetic cartilage, which will, and just to kind of refresh your memory, to replace this kind of a structure. And so I think I'm running out of time, so I'll just wrap up with some conclusions. First of all, polymers are very versatile materials that can address multiple needs in medical devices as well as other applications. Copolymers increase material versatility because you can now customize the properties as you need. If you need a little bit more hydrophilicity, you can introduce that. If you want more toughness, you can introduce that. And the horizon in such materials is ever expanding, because if we thought that, oh, there are tens and thousands of polymers, now there are millions of the combinations of these different polymers that you can create, and each can have its own unique set of properties. So the application is only limited by our imagination. We can create anything that we need in order to do this. So I would like to then close my talk with some acknowledgements. I would like to thank the organizers of this symposium for giving me an opportunity to present here. And since it's very appropriately for the chemistry teachers, I have to acknowledge some of my teachers. And the first is Professor Prabhu, who, if I'm not mistaken, sir, I was your student in your first lecture on chemical kinetics in 1973. So, you know, it is an honor and a pleasure to have been associated with you all these years.
Yes, indeed.
Thank
you
you.
were the first student in the BSc class.
Yeah.
1974.
Yes. Yes.
A very good student.
And the second is Professor Barton, James Barton, who was a professor at Wilson College, where I did my BSc, and a department head of Woodstock School. And I would like to just mention a brief anecdote on this, and that is, you know, like many students, I really did not know anything about chemistry. And so I had applied for IIT after my inter-science, and then I took an application for BSc in Wilson College, and I was admitted into Wilson College. And the very first lecture he taught on electron configuration fascinated me so much that I fell in love with chemistry. So much so that I got into IIT, but I refused it. I stayed on to do my BSc in chemistry. So I think that teachers who can inspire in that manner are what keeps this academic profession so very vital. And so I wanted to mention that. And last but not the least is Professor James McGrath, who is no more, but he was my research advisor for my PhD. And I have learned so much from him on polymers, the concepts, how well he taught the topic during my thesis work. Stays with me today. So he lives on in the work that I do, and as well as all his other students. And with that, I would like to close this talk. Thank you very much for all your attention.
Thank you, Dr. Venkata Narayan, for your highly impressive presentation. I think we are all highly we have to admire you for your presentation, and we are all got a lot of information about on polymers. And I think Dr. Prabhu is especially, he must be very happy to hear his students, former students in such a high place, and also giving
very-
them such a lecture.
Gives very
And
pleasure
thank
to
you,
a teacher.
Mr. Venkatanarayan. Yeah.
It's an honor to listen to my wonderful student, Dr. Venkat,
Yeah,
one of my
it's a-
best students.
Thank you, sir. Thank you.
Yeah.
Very much honor for a teacher.
There may be, I think Dr. Venkanan would like to interact with some of the participants if they have any question.
Yeah, sure. If there is
Yeah.
time, I will be glad
Yes,
to.
participants, please come forward if you have any query to Dr. Venkatanarayan.
Participants, you can raise your hands or you can just write your question in the chat box. I will be reading that for sir. Okay.
In the meantime, Dr. Venkatanarayan, I can ask you a question.
Sure.
Just like I want to share my views, it's really a lot of information I got about this lot of application of structure, chemical structure. Particularly, I am fascinated by the chemical structure, all these things. Just like you have block polymers,
Yes, sir.
having one block conducting, one block non-conducting, no?
Yes.
So in your block polymers, you have shown that there is some air gap which increases the resistance, right?
Yes.
So in another way, suppose in block polymers, if one block is insulating and another block is conducting, like AB,
Yes.
A block is conducting, B block is insulating, then maybe there is a lot of application like that, right? So
Yes.
zigzag current is passing zigzag way, not a
Yes.
straight way, right?
Right, right. And there are a lot of these stacks. They actually create a lot of stacks which would do the same thing. Yeah. Yeah, you're
One
absolutely-
more thing I'd like to know from you. What is the problem? See, we consider polyethylene as a environmental hazard or pollution for many wildlife or many aquatic lives. Now, what is problem with recycling of polythene? That point is not clear to me. Why not we can recycle polythene again and again instead of disposing to the environment? What happened to the polythene? Because polythene is the simplest structure of polymers.
Yeah.
And people say that, polymer chemists say that it cannot be recycled many times. Once recycled, its color is given black so that it cannot be used for food packaging, all these things. I don't know much. Can you enlighten us on this aspect?
Sure, sure. See, one of the things is that polyethylene has been used in a lot of very, very thin films, which, I think when it is disposed in as garbage, it's very difficult to recover that. But, if it is, there is no reason really why you cannot recycle polyethylene. Because polyethylene is a thermoplastic material, which means that, let us say you take the material and you heat it up, it will again flow and you can remold it into a different shape. Now, the other advantage that polyethylene has, now, from a recycling point of view, one of the reasons that it becomes a problem in the environment is that it is a completely inert material. So you can think of all your strong acids, strong bases, nothing will affect it, and which is why it is used in all the chemical resistant piping and so on and so forth, because nothing chemically reacts with polyethylene. So therefore it is not biodegradable. That's the disadvantage. On the other hand, the advantage is, and actually I think it's not that it cannot be recycled. I think that people have to invest into the infrastructure that can actually chemically treat
Sir.
it, because whatever is present along with polyethylene can be leached out using very aggressive solvents, aggressive chemicals, without affecting the polyethylene. So that one step is needed to separate the polyethylene from everything else. And once you do that, you now have polyethylene can be remolded and reused. So, but nobody seems to have the appetite to do that one extra step. And I think that is the biggest disadvantage. I don't think we can blame polyethylene for it. I think we have to take the blame for not investing in the in infrastructure to create a very aggressive, because you can use, for example, say for example, something dissolves in a solvent like xylene, for example. Okay. Xylene does not dissolve it. It does swell up the polyethylene, but it does not dissolve it. So if you take that and you treat whatever is this mixture of a pigment and in polyethylene, you can actually leach out all the pigment. Now you have the polyethylene, you can do that. So there are ways of doing it, but it calls for more money and more time and more investment. And if people don't have the appetite to do that, it's easier to just throw it out.
So that is the thing. People are not interested, just shouting that polyethylene is very hazardous to environment, but we are not interested in investing for the sake of environment.
Yep.
Yeah, that is the thing. So companies like yours one, they should come up with some research and how to lower the cost, etc. Okay,
Certainly.
thank you, Dr. Venkata Narayan.
Thank you.
So now
I don't know if there are any more questions, or is it? Are we done?
Sir, we have a query from Shanta Kundur. I'm unmuting her. Ma'am, please unmute, accept that request. Yeah.
Sir, thank you, sir. Thank you for giving me this opportunity. Sir, good morning, sir. Venkat, sir.
Good morning, ma'am.
Sir, I heard your lecture, but I have a small doubt. In synthesizing the alternative polymers and copolymers and the random polymers, is there any special method to decide the path, whether we are going to get the end product as a random polymer or an alternative polymer? Sir, can you clarify?
I'm sorry, I couldn't hear you.
Are
There's
you
some
seeing
crosstalk.
any screen am I shared by me?
Sir, the question is, hello, sir?
Yeah,
Am
go
I
ahead.
audible? Am I audible?
You are audible, but I'm hearing somebody else's voice.
Sir, you classified the copolymers as the alternative copolymers and random copolymers. So when you are synthesizing it, how do you decide that, or how do you identify that we are going to get alternative polymers or random polymers? Is there any mechanism to have an end product in the desired direction?
Yes, that's an excellent question. For example, I gave you an example of it depends upon the environment in which you are interacting the two monomers. So, for example, like I showed the styrene maleic anhydride. Maleic anhydride cannot homopolymerize, and there is a property called relative reactivity ratio, which means that you have the propensity of a monomer to react with another monomer. So, for example, if you have a styrene molecule and a maleic anhydride, then there is a certain activation or a thermodynamically favored pathway for styrene to react with another styrene molecule, maleic anhydride to react with another maleic anhydride molecule, or styrene to react with a maleic anhydride molecule. Now, in this case, what is seen is that the probability of reaction of a styrene with a maleic anhydride is so much higher than the other two that it favors an alternate copolymer structure. Now, another way of doing that is that you influence the architecture by appropriate choice of solvents and catalysts. So there are some catalysts that are not will not activate one monomer type, but only another monomer type. So it starts the reaction with that. But then that monomer cannot continue to propagate because of reactivity ratio consideration. So that is how you design. So a lot of this is there's a lot of data that's been provided in literature on what are called reactivity ratios. And these reactivity ratios are a function of the chemical functionality on the molecule, as well as solvents and initiators or catalysts that are used. So by taking an appropriate choice of some of these, you can actually design which way you want the molecule to go. Now, in
So
the
the end
case of
product, looking into the end product, we have to design the environment for the reaction.
exactly, yeah, right.
Okay.
So
Right.
that's how you do. So the other way of doing it is, like, if you want to do the block and the graft is more straightforward. What you do is you have what's called living polymerization. So if you have, let us say, 100 units of one monomer, and you add the living polymerization catalyst, then you only have these 100 reacting with each other, and at the end of it, the reaction is not terminated, it is still active. So at that point, when you have given enough time for all the 100 to build up into the chain, you now add a second monomer to this, and that now attaches to the chain end of the first block and grows to the length you want. And then you at the so you calculate how many moles you have to add. So that's where stoichiometry becomes very important.
Yes.
Thank you, Dr.
Thank you so much,
Venkata
sir.
Rama Narayan. Because other speaker may be waiting.
Yeah. Yeah,
So thank you very
right.
much. Let us thank Dr. Venkata Narayan for his excellent presentation and illuminating lecture. Lot of information we got. Thank you, Dr. Venkata Narayan.
Thank you very much. Thank you very much.
Yeah. Now we would like to hear the next speaker, Professor Saurabh Pal. I think he may be waiting.
Yes, sir.
Yeah, I request the convener, Dr. PM Mishra or the Amrit Mitra, to introduce our
Yes,
next
sir.
speaker, Professor Saurabh Pal.
Okay.
Please.
Thank you, sir. Thank you, Venkat, sir. Actually, our speakers are so eloquent and mesmerizing that we don't want to let them go. We want to continue listen to them and learn more and more things from them. Thank you, sir, for your wonderful lecture. Our next speaker is Professor Saurabh Pal, sir. He is the director of IISER Kolkata. Professor Saurabh Pal, sir, was the former institute chair professor at IIT Bombay. He was previously the director of CSIR NCL Pune. The research interest of Professor Saurabh, sir, is theoretical investigation of hard-soft acid-base relation, study of electron-molecule scattering, development and application of molecular dynamics, density functional response approach for molecular properties, and computational material science. Sir has been awarded with several prestigious awards and honors from several reputed organizations across the globe. To name a few, Sastra C.N.R. Rao Award in Chemistry and Material Science from CSIR in the year 2014. Sir was the recipient of the prestigious Shanti Sharup Bhatnagar Award from CSIR in the year 2000. Sir was the J.C. Bose National Fellowship from DST in the year 2008. Sir was the Fellow of the Indian National Science Academy from Indian National Science Academy in the year 2003. Sir was the Fellow of the National Academy of Science from National Academy of Science in the year 1998. Sir was also the Fellow of Indian Academy of Science from Indian Academy of Sciences in the year 1996. May I now welcome Professor Saurabh Pal, sir, to take over. Thank you, sir.
Yes, Professor Saurabh Pal, you are please welcome. Please go ahead with your presentation.
Hello.
Huh.
Mishra sir, I just got disconnected and I'm back. To whom I have to provide co-host rights?
Saurabh Pal, Professor Saurabh Pal.
Okay. I am just providing it.
He is on the screen, Professor Saurabh Pal. Yes, he is on the screen.
Dr. Pal, you can unmute yourself. I have provided you co-host rights.
Okay.
Yeah.
Thank you. So I hope you are able to hear me.
Yeah.
Yes, sir, you're audible.
Yeah. So I'll try to share my screen. So I should go to my screen. Is it to the screen or whiteboard? Yeah.
Sir, your screen is visible. You can just shift to the PPTs. They
Oh,
are
okay.
visible to the.
Is it
Yeah.
visible now?
Yeah, yeah.
Yeah, it's visible now.
Yes,
Sir, I request you to
Okay.
please activate the
Yeah.
slideshow.
Yeah. We'll do that. So. Is it visible?
Yes, sir. Yes, sir.
Okay. So let me thank the National Chemistry Teachers Association for this conference or the convention, as they say, for this 2020. I think it has been a great pleasure because I am kind of connected with the journal that the Chemistry Teachers Association has been publishing as in the editorial board. And of course, connected with Dr. Prabhu for a very long time. I can't remember how long back. And I have been in Mumbai, Pune, so I have gone many times and gave talk. So Dr. Prabhu has been a very good friend. You know, I have given talk in Wilson College. I think Dr. Prabhu will remember. Several times I've been there. So it has been a great pleasure. Now that, of course, I'm in the other part of the country, at least for a short duration, I would definitely get back to the western part very soon. But it has been a great pleasure that he has invited me, and I'm very happy to address all of you in this National Convention of Chemistry Teachers. Since I am also in the Teaching Institute, I gave a title of Integration of Research and Education in Science in general, but I'm going to focus on chemistry. So chemistry is undergoing a lot of change, and I'm going to talk about specifically teaching in chemistry, how is it difficult, and then I'm going to talk in the last part how computational science is integrating today, not only research, but also teaching. As all of you know, many of us are teaching online. This meeting is going on online. So I think it has been a great integrating force. And with that excuse, I'll also tell a little bit about my own research. So I have been now in IISER Kolkata for more than 3 years. I've already got into the 4th year. I have, of course, been in NCL, as I said. That is the time I interacted with Dr. Prabhu and the National Chemistry Teachers Association for a long time. I just finished my tenure at IIT Bombay this month when I turned 65. That was the retirement at IIT Bombay. And currently, I'm also associated with Ashoka University, Sonipat, as a visiting professor. And I think they are also starting chemistry. I must say, Ashoka University, many of you might have heard, it's a school of liberal arts, but now they have started science, and very recently they have started chemistry as well. I think it's very good for chemistry that I think chemistry is getting its due importance. So let me quickly talk about the integration of research and education. So this is a very quick slide of the 3 cities in which I have lived. I don't have to explain to all, Pune, Mumbai, Kolkata, where I have primarily done my research. As we are talking of research and innovation, I think I have to say that I am in one of those institutions which was built with the idea of research and innovation in science. So that is, of course, the Indian Institute of Science, Education and Research. Many of you, of course, know this. In fact, I'm very happy to say that Kolkata and Pune started at the same time in 2006, and next year will be actually 15th anniversary of IISER Kolkata and IISER Pune. And I'm very happy also to say that the Wiley has actually approached me to guest edit along with Jayant Udgaonkar, which will a publication, a full issue in Chemistry Asian Journal. Many of you have heard about Chemistry and Asian Journal. It's a very good journal by the Wiley, where they will focus on the research papers of Kolkata and Pune, faculties exclusively of Kolkata and Pune. That I think is a very singular honor, where a journal like Chemistry Asian Journal is focusing only on the institutions. So I must announce that this came very recently, so I'm very happy, and I'm sure Jayant will also agree that it's a proud moment for both the 2 IISERs. All right, so I think I just wanted to tell that there are other IISERs which have come up subsequently, like Mohali, Thiruvananthapuram, Bhopal, and then very recently Tirupati and Berhampur. So there are 7 of them right now. And I think they are primarily administering BSMS and, of course, PhD degrees of the kind integrated PhD and normal PhD. We do not have 2-year MSc course yet as a general policy, but I think in very focused areas, we plan to start 2-year MSc course. We already have in Kolkata 1 in space physics, But other than that, 2-year MSc program is right now missing. So it's a 5-year BSMS program. That is our focus program. Okay. So this is, of course, the Kolkata campus. It's a 201 acres campus, and it's spread in 201 acres. And we have been ranked quite high. Our latest ranking in overall ranking in NIRF is 29, and we have gone as high as 24 in 2018. So I think we are somewhere in the 20s to 20 to 30 bracket. It's pretty good, and I believe that as days have gone, Pune and Kolkata are taking their own space in science education. As far as chemistry is concerned, I would like to ask this question: where is it today? Where is the hierarchy of chemistry education? Because I have been teaching chemistry with several students at IIT Bombay. I have actually been teaching from Pune University. Many of you may not know that although I was in NCL, I used to teach in Pune University. Then IISER Pune came up. Then I started teaching in IISER Pune. Then, of course, in IIT Bombay, and today in IISER Kolkata. So I have been kind of teaching in various institutions, and I really feel that the chemistry education is at a crossroad. And that is what I want to tell you why. There is a hierarchy of chemistry education. Of course, everybody talks of integrating research with education. That's the easy thing to talk about. But it's a very hard thing to do. How do you integrate research, and what is research in chemistry? That itself I'm going to come to with education. Of course, with COVID-19, there are more challenges in science education in general, and there are opportunities. Of course, we can see the opportunities today that without traveling, I can easily speak in this particular convention. The online teaching is here to stay for some time, but is it being done properly? And I think that's squarely I will ask the question. And I think people are not taking the online education as seriously as it could be done. I know there are problems, but I think it could be done better. Of course, evaluation is not the only issue. Let me first tell you why we do science, because science, of course, all of us know provides the basic expertise, and the physics, chemistry, mathematics, biology, etc. They provide platform. And today, when you talk of interdisciplinary research, I think we should not forget the basic science, the fundamental of physics, chemistry, mathematics, and biology. Without that, no interdisciplinary research can take place. And I'm very strong about it. You must have a very good base. So, but after that, when the platform is set, are we able to move to interdisciplinary research? And that is where our lacuna is. We are not able to move there from the discipline-based to interdisciplinary research. Whereas discipline is required in the early education, is very important to know how do you move to the next level. We have lots of interesting options, like people can do academic research, teaching, industry, alternate science career. But I must say that I took up science because of the last point. I didn't realize what can science do, but I just thought science fulfills my mind. So I was very happy to do science, and that is the reason I took up science. Today, of course, for the students, you have to motivate them. All the teachers who are here, you must motivate them. Why should they take up science? So, of course, one of the reasons is jobs, obviously. So there are academic institutions, as I have listed some of them, research laboratories, I have listed some of them, and many of the institutions like IISc, IACS, they're actually moving to educational platform as well. Then there are mission-driven research like atomic energy, space, defense. So there you have a goal, and many people like to be in those missions because that's a big pride for the nation. Of course, industry R&D, that is very, very important. And Dr. Venkat was giving a talk on polymer, but there's so much of interest from the industry. I mean, polymer research has been driven by the needs. So industry is, of course, very important, but even equally important is the entrepreneurship. And I think this I want to classify along with away from industry R&D, because industry R&D is another job. Entrepreneurship is where you create jobs. You don't look for jobs. And I think that is something the students have to be told in colleges today, that all of them do not have to look for jobs. Some can create jobs based on what I call deep innovation, not necessarily jugaad. It's a deep innovation, which is a high science innovation. And I'm going to come to that very famous quadrant, the Pasteur quadrant, which is very, very famously known. The fundamental science, of course, is a curiosity-driven research, as most people think, but very often it cannot be predicted. And many times it is due to necessity, accidental, and so on. Like, for example, the Archimedes discovery, I always classify as a necessity-driven research, simply because Archimedes was forced by the king, and you never know what the king would have done had he not come up with his famous discovery of how to find the density. So basically the volume of an irregular substance. Accidental research like urea, synthesis is an accidental research, and many. Curiosity-driven research, like, of course, the most famous is Isaac Newton himself, when he saw the apple falling. So I think people have to be told that it is very difficult to predict where the fundamental science is going to come from. And many people discuss in this country, what is the next Nobel Prize, and so on and so forth. You really cannot tell how the science can be done. I mean, many people have their own ways of doing science. And the problem is, of course, not just doing fundamental science. Along with the fundamental science, you have to translate those science. And that is where the Louis Pasteur quadrant is very, very useful. It is called use-inspired basic research. Edison quadrant is more of an applied research. And Bohr quadrant is, of course, a very high fundamental understanding. In fact, many people in India have moved into Bohr quadrant. I mean, they're doing good science, but they have not been able to move here. And that has been a big problem. Those who are here doing very well in applied research have not been able to move the applications or even the entrepreneurship based on a deep innovation, which is high science. I think that is the very important part, to do new science and then do the applications. Of course, when you talk of Nobel laureates, the Indian and Indian origin in science, we have four of them, of course, many of you know. So C.V. Raman, who is the only one who did from India, though, Chandrasekhar, Hargobind Khurana, and Venki Ramakrishnan. And we always discuss where will the next Nobel Prize come from in India. And I think that is very important. So we have to catch up with the Western world in terms of developments of science, education, research, and technology developments. But let's not forget that the ancient Indian science, and that includes chemistry. There are a lot of chemistry which was done, in fact, in the Ayurveda, you will find the ancient science was very strong. The chemistry was also very strong. Somehow down the line, we forgot them. We, of course, need to think today beyond that. It doesn't matter what we had, and more rationally you have to think. But let's not forget that there are the inventions like zero, number theory, Ayurveda, geometry, algebra, computer algorithm. They're all existing. In fact, computer algorithm, you will not believe, before the Western algorithm came, actually existed. I have myself seen an algorithm from very old Indian era. I can't remember what was the exact year, but before the computer algorithms actually came, on a solution of a algebraic equation, which is a quadratic or a cubic equation in general. So I think it is very good that we had, but today we have to think beyond and see what we can do next. As far as chemistry is concerned, it's very important, as far as chemistry is, I'm sorry, just lost the screen. Yeah, just 1 minute. As far as chemistry is concerned, I must say that it is very difficult to teach chemistry in school. I don't know how you feel. Many good school students do not take interest in chemistry. I think you must have all said, this is something that is said. I have sat in the various interviews like KBPI and so on, and I have found that the very good students, they're interested in physics and today in biology. Physics and biology have often been the choice and not necessarily chemistry. And I mean, this may be a debatable point. You may have a different views. It is because I feel that when we grow up, we do not have any instinctive knowledge of chemistry to start with. And chemistry looks very complex. Whereas physics and biology are subjects which you feel everyday life. So physics is something that you are seeing every day. The cricket ball, I mean, you are looking everything physics. Biology is something that you also feel, the zoology, plants, and so on. But in chemistry, you don't see molecule. You don't know what is the reaction, except that there is a color change, some properties change, which are very difficult to show in an ordinary household. So chemistry has been taught by transfer of knowledge. That has been the most popular process, and not necessarily by actually feeling. In fact, there is a considerable evidence that both learners failing to make sense of teaching and the students developing alternative conceptions of the material presented to them. So what teacher wanted to present, students have understood something else. And that has been a problem in chemistry. When they go up, they suffer from various things. So although chemistry is seen as a single discipline, but it has the most diversified approach. In fact, it is hard to believe that most physical chemists are working within the same paradigm as most organic chemists. In fact, I feel the paradigm with which physical chemists work is different from the paradigm of organic chemistry, though both are chemistry. Organic chemists have different way of looking at synthesis, more intuition based, but physical chemistry is probably more related to physics than the physical chemistry, than the chemistry. Perhaps the same point can be made of other subjects, but physics somehow seem to have a commonality of approach. Whether you do classical mechanics, electrodynamics, classical quantum mechanics, there is a commonality of approach. The concepts are different. But in chemistry, even the approach is different. And I think that is a very, very difficult problem. That is why many physical chemists find it very difficult to engage themselves with organic chemistry and vice versa. And that has been one of the major problems of integrating chemistry. Biology, on the other hand, is a very broad discipline. But again, to understand biology, you need to understand chemistry, physics, and today, I must say mathematics in biology because of the importance of the data science. So in fact, a hierarchy of sciences are building today, and I think that is very important upon each other. Very common hierarchy is that the physics is built on mathematics. I don't know if you'll agree. If you are doing physics, they say, oh, you must be very good in maths. Then the hierarchy is that from the physics you come to chemistry, and from chemistry you come to biology, and from biology you come to psychology. This is a very standard hierarchy, but I try to tell that this is actually completely breaking up. So there are a large part of biology which make no direct or indirect application of chemistry. Biology, in fact, directly goes from mathematics today through the data science. Many of you know data science. Physics is also relied on chemistry, like development of new materials require very good understanding of chemistry. To say that chemistry is built on physics and not the vice versa is also wrong, because today physicists need a lot of chemistry on the new material. Psychology certainly builds heavily on biology and chemistry. Cognitive science and neuroscience are probably the best conceptualized as parts of life science, however. When you teach chemistry, the other major challenge that you have is to bring the chemical language. So it is essential to distinguish between chemical experiments and chemical language. Chemistry has a language of its own, which is again very difficult to teach. There are lots of things that I can talk on chemistry education. In fact, I remember quite some time back, I talked about chemistry education in a Homi Bhabha Science Center a few years back. One should read some of these titles of Nature of Chemical Knowledge, History of Chemistry, Models and Modeling in Chemical Education, Learning Chemistry in a Laboratory Environment, Chemistry Curricula for a General Education. Many of these have to be discussed. The roles of chemistry in vocational education, that is very important. Because today with the new educational policy, you must have seen that there has to be exit policy for everybody. So people who are doing first year of BSc, they can go out and they should be able to make their career. So I think the role of chemistry in vocational education is very important. Can there be an informal chemical education? Because chemistry is taught too formally because of the language. Unless you know the IUPAC language, it's very hard to do chemistry. We should have a context-based approach to the teaching of chemistry. And I think I want to talk because there are so many teachers today. What are those context-based approach? What are their effects? The particular nature of matter, for example, challenges in understanding the submicroscopic world. Problem solving in chemistry is very often neglected. Chemistry is taken as some information. But physics, for example, does better in terms of problem solving. The teaching and learning of, let's say, chemical equilibrium, chemical kinetics, electrochemistry, from chemical energetics to chemical thermodynamics, how are they connected? And I think it's very important to explore these. And to do that, I believe the teacher's knowledge also has to be expanded. Research and development, of course, for the future of chemical education. Because today, when you do organic chemistry, that's a chemical reaction. Are they not connected to thermodynamics? Are they not connected to kinetics? So how do you do this connection? And that is where the difficulty in chemistry education. I always believe that's the reason it's tough. On the other hand, when you say integrate with research, we have to understand research itself is changing. from structure to function. Old time chemistry was nothing but molecules, and then look at their structures. Today, you do not synthesize molecules. Just like that, you first look at the function. What do you want to do? And then do a retro thinking, and then this synthesis would come at the end. Why am I synthesizing? I used to be in many project meetings. Many of the titles of the projects are very simple: structure and characterization of blah, blah, blah. And again, it keeps on. But you don't ask the question, why are you going to synthesize this? Why are you doing this? So I think that is a very major challenge that the chemistry has faced, and today it is changing. So this aspect has to also get back into the education. How do you think in a retro manner from function to the structure? How do you break the traditional discipline? Again, come back, organic, inorganic, physical, biochemistry. How do you break it? It's very hard to find a teacher who can teach physical chemistry and organic chemistry. I don't know. What is your experience? It's very hard. Why is it so? Why are we not able to break these traditional barriers? I think that's another question that you have to do. So research has been driven by emerging trends in research, technology, and by societal needs. And that is a very important thing that chemistry has been driven very recently. Societal needs has become very important today. So that's why you talk of many problems which will come. Then the next important appeal to me, to all the colleges, and of course to the universities, is you must have a history of science, history of chemistry as a curriculum. I think we tried that in ICER. I remember, when there was a ICER meeting. I'm sure if Dr. Sivaram has already joined, he would remember. We had a meeting in 2006 in Pune, NCL Pune, and we tried to say that history of science must be pursued as a curriculum. In fact, ICER Kolkata started, ICER Pune also started, and eventually everything got a little bit diluted. And one of the reasons they tell me is that very hard to get a teacher. And I think that's really a serious problem. Who can teach history of science in particular? The story of Archimedes, Newton, Einstein, Avogadro, Faraday, Lewis, that's a fantastic story. And those are the stories which should inspire the students to take up either physics, chemistry, biology, mathematics, whatever. So lots of things that have happened in chemistry, from 1770, the Lavoisier, then atomic theory, molecules, Avogadro law, urea synthesis, benzene, periodic table, electrolysis, the Davy. Electron, it's amazing that the electron came 100 years after the battery. Battery was discovered 1800, electrons came in 1897. So today it looks amazing. Radioactivity, plastic, polymer, a lot of talk was given by Dr. Venkat just now. And of course, the modern chemistry, which started with Niels Bohr, Bohr's theory of atom, and eventually to the quantum mechanics. Before that, G and Lewis chemical bond, and then of course the quantum theories, which actually today are the state of art in understanding molecules and atoms. With these as the basics, where do you go? And that is where the research comes in. What are the future challenges that we can handle? And obviously those challenges are driven by societal needs today, as I said. So renewable energy, for example, is a very important challenge. And I think most of the research in chemistry is being driven by renewable energy. And what I mean by renewable energy is, of course, using resources which are sustainable. So sustainable resources are very important, like solar, hydrogen, bio resources, and so on. Processes which are energy efficient. And I say the buildings, for example. Can we make buildings which are energy efficient? And even that we are not able to do. Buildings which can take care of its wear and tear automatically. In fact, there is a journal which is called Sensor and Actuator. So it must sense on its own and start actuating, correction. So those are called what I call smart materials, smart buildings. Of course, environmental friendly processes, which you call green chemistry in another way. Affordable healthcare. Cultivate affordable healthcare today, of course, everybody understands what it is. Because affordable healthcare is a very important point, and today in the corona, you can see that even if we can take care, for many people it is so expensive. Cultivation of farms, with a minimum land water, can you have maximum crops? Technology-enabled defense system, many of these chemistry is going to play a role. It's not that the chemistry alone can do, and that is where I say it will require interdisciplinary expertise of many subjects. Again, looking at many of the institutions, including IITs and so on, we are not able to bring together this expertise in the way it should be done. For sustainable resources, I have just put down certain things like solar, conversion to heat and electricity, wind energy, fuel cell, which is from hydrogen, bio-waste to alcohol and fuel. A lot of people are working into this today. Hydrogen, of course, I already talked of, nuclear energy. But a very important part that you must have seen everywhere is now CO2 to fuels. And a lot of projects which are going on, reduction of CO2 down the line to methanol, for example, to methane and so on. I mean, it's an amazing thing that we can do with the CO2 itself, because it does a lot of job together. Not only it removes CO2, it also adds value addition. But of course, when you say CO2 removal from the environment, this is not going to help, because this is still a very small part. It's of course going to build fuels and chemicals, but we have to find ways of cleaning the environment. And I think this is where, when the post-COVID, I would say we must start thinking of protecting environment and climate. I think that's the very important part. So bring in all kinds of technological innovation to protect the environment and the climate. You require more of digitalization. And that is very important. Now that's already happening, as you can see. In fact, nobody ever thought we can have meetings in Zoom, Google Meet. I mean, why was it not possible before? They were there. But I think that's the kind of opportunities that the COVID has thrown up. And today we are having even discussion, many of the meetings where people could not think without doing closed door meetings, that those are possible. People are doing online. And of course, for education. Education online, although there are several questions that have come up. How good are we doing? In fact, I myself doing a survey at ISER from the students. How good is the online teaching? And I find very mixed response, to say the least. Of course, evaluation is a problem. How do you evaluate them? Is a big problem. People are talking of proctored evaluation. There are still problems there. But the big thing is that you can't teach anytime, anywhere, to anybody, anything. I mean, that's very important. That people can attend any classes from anywhere in the world. So it has opened very large learning opportunities. Technology-enabled tools, of course, is going to come. The bigger challenge is how do you do experiments, chemical experiments. In fact, people are still talking about technology-enabled tools to replace hands-on experiments in number of cases. And that is an immediate feature, because we are still grappling with how do you conduct the lab courses. I mean, there is a theory part. I'm sure all of you must be thinking of it, but can you completely replace hands-on without students coming to the campus? So I think these are some of the challenges that we have to do. In the new normal, we'll have opportunities to have innovative solutions, protection of climate and environment, thrust in research, virology, particularly virology and pharma, smart materials to make life easy, communicating subjects, innovation in education and laboratory. So I think that's something that I want to tell you. However, in last, do I have about 10-15 minutes? Yeah, because I started a little late. So I hope I have 10-15 minutes. Yeah? So
Yes, sir. Yes, sir.
Yeah.
Definitely, sir.
yeah, so what has happened is the computer, and I would say computer has certainly provided an enormous opportunity. But in terms of science, I will say that the computational science already existed, which is based on computer. And I want to distinguish between computer science and computational science. Computational science is certainly use of computers, but actually to provide solutions to science. And that is where you require theory, you require experiment, and you require computer. And together we provide solutions. So this has become an integrator. This was an integrator in science long back. And today we are realizing that many computer-aided tools can come in to bring in many other technological innovations. I must say two very important quotations, which I really love to show. One by Kotelek, both of them are 200 years back, as you will see. The more progress physical sciences make, the more they tend to enter the domain of mathematics, which is a kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculus. So you can see the importance of computational science 200 years back when quantum mechanics was still not there. Let's not forget, quantum mechanics came in the early 20th century, mostly early 20th century. But it was not even there in the 19th century, but we already talked of the importance of computational science. But read the next one, the Comte, 2 years after, actually. Every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. Very interesting. if mathematical analysis should ever hold a prominent place in chemistry, and then he says an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So you can imagine how was mathematics viewed in the context of chemistry. So that has been a big challenge. I'm not even talking of biology. But today we know that the computational science is very important in chemistry. So of course, I will have to go back to Katel's statement and not this Comte's statement, which what has actually held it. Today, using theory, computers, and fast algorithms, we can solve complex equations from theory, predict structure and properties of molecules, reactions between molecules, dynamics of evolution, biological evolution, chemical evolution, modeling new materials and drug design. In fact, people are even doing drug design. Lots of biological activity and tools of artificial intelligence and machine learning. And that's very important. Today, AI and ML are going to play a very important role. In fact, the theory, modern theory started even before quantum chemistry by G.N. Lewis. I must say, G.N. Lewis is a very famous paper, The Atom and the Molecule in Journal of American Chemical Society. But you have to remember, when the octet rule came by Lewis and Langmuir, the quantum mechanics was not there. When quantum mechanics came, G.N. Lewis actually left the field. It was Linus Pauling who actually took over for the valence bond theory. And today, we now have theories at different length scale, from quantum mechanics or approximate quantum mechanics to molecular mechanics to coarse graining and so on. So depending on the courses, we have horses. So I say horses for the courses, just like in a horse racing. So depending on the system, we use theory. However, the two different kinds of theories like quantum and classical, this was there long back. In fact, Niels Bohr already said in the limit of Planck's constant going to zero, quantum principles go over to the classical. In fact, all of us read those. So that is where atoms and molecules can go to nano, bulk, and so on. So the classical lies. So this is the bottom-up approach. So define theories at different length scale. And this is a slide which will actually tell you at different length scale, at the small length scale and small time, it is the quantum mechanics. That's what I call by ab initio. Then you have molecular simulation based on atoms, atom-atom potential. Then for the polymer, for example, people are looking at mesoscale simulation. Just now there is a talk on polymer, and I'm sure Dr. Sivaram will also talk on polymer. People are looking at groups of atoms interacting with another group of atoms because it's too big. So they are called beads, and that is why the coarse graining or mesoscale simulation is coming. And then, of course, the engineering length scale, which was actually historically developed earliest. But today, what is important, can we understand from quantum mechanics to the engineering length scale, how the approximations have been built, and that is a major challenge today. But we know that depending on our system, we have the theory. And that is a very good thing that has been propelling the computational science. One of the things that got Nobel Prize in 2013 was a mixing of two different theories. And I must just give one small example. It is called QMMM, let's say. It is a quantum mechanics and molecular mechanics. So for example, I have a complex system in which a drug is binding. So let's say it's a membrane and a drug binds here on the blue region. So the binding energy between a drug and a biological system is extremely small. So one has to look at that as a completely different way. So that has to have a quantum mechanics part. So the blue region is being treated in the quantum mechanics. Then there is a blue to green region, which is basically the interface region. And then finally the classical mechanics. So on the same system, we are using quantum mechanics and classical mechanics, molecular mechanics. And this has to be very carefully monitored, the interface region. If you can do that, the results are very good. And so you have best of everything. Because for the large system, long-range interaction, you don't need quantum mechanics, but you need quantum mechanics here on the interacting side. So this is a situation where we are actually bringing in the best of both. So that's the main idea, which is actually getting up. For a large system, most of the quantum mechanics today are based on density functional theory, which is a method of choice in materials. I will not talk about the details, but there are a lot of things that are happening, including Minnesota functional, dispersion correction, and thoughts on the basis sets. I will skip this, but I just wanted to tell that depending on your systems like atoms, molecules, to solids, you use different kinds of method, different kinds of basis set, like atom-centered or periodic basis set. But very often, for large molecules, DFT is this method of choice, density functional theory. For small molecules, you have very good methods, which are better than DFT, which are ab initio methods like coupled cluster, where I have done a lot of work, perturbation theory, CAS SCF, and so on. I'm again not going to talk about all those, but I just thought today we have an available set of tools depending on what the system is. Let me not talk of the simulation, but let me say that with all these, we are very good today in doing chemistry. So one of the chemistry that we can do, and I've been working with my collaborator, I'll name her later, on a design of catalyst. And I think that's a very serious problem. Can you do a computational design of catalyst? So it has several components, like selection of metal, pre-catalyst, sometimes there are co-catalysts, additives, substrate, reagent, solvent, and so on. You know, today, I don't think computational chemistry is still good enough to do everything, but I think we're able to break through. And with the help of computational chemistry, we're able to find out which catalyst would give the least activation barrier. And I think the barrier is very important. And we are able to do a reaction mechanism. In fact, many organic chemists are using this today. So that's a real possibility. We have worked on metal clusters, very simple metal clusters. And I must quickly say that we have looked at gold and silver cluster. They show exciting properties. In fact, if you look at 8-member gold, it's inert, but monodoped silicon, it becomes catalytically active. Such a simple thing. And that happens in cluster. One atom change can make complete change of properties. So AU8 is inert, but Si87 is very, very active in oxidation reaction. Pristine gold cage, AU18, gets activated by metal inside the cage. Hydrogen, chemisol, gold and silver cluster. Aluminum cluster for dinitrogen activation. And we have particularly looked at aluminum clusters on boron nitride doped graphene. It's a very, very good cluster that we have seen. This is, for example, AU18, just one reaction we are trying to show. CO oxidation reaction. As you can see, CO with oxygen going to CO2. That's the reaction we're looking at. And this is the complete cycle on AU18, intermediate, a transition state, intermediate, another transition state, back to the product. And you can look at the barriers of 0.71 and 0.45. You look at the next one, which are now metal inside the AU8. You can see how quickly the barriers drop down. In fact, sodium is very good because it drops down the barrier, though sodium is extremely difficult to synthesize. But I'm sure magnesium, calcium can be synthesized. They will do a very good job. So you can see same gold cluster, you put some doping. In fact, all of you know that doping is a very, very useful strategy in material science. And using that, we can design catalysts. I'm just giving one example. Another example, same CO oxidation reaction. We looked at gold clusters 6 and 8, atom gold cluster, and very high barrier. But as soon as you do hydrogen chemisorption, it's a pre-treated with hydrogen. And this is experimentally synthesized today in gas phase. It's very, very hard synthesis, but one can do that. You can see how low the barriers are. In fact, AU6H is almost barrierless. So you can do very enhanced oxygen activation. Before I give one more example of a material, which is hydrogen storage material, I would say I have worked a lot on hydrogen storage, and particularly metal organic framework and magnesium, but both of them are not good initially because one of them is physical absorption, another is chemical absorption. What we require is a reversible storage material between chemistry and physics, chemical and physical absorption, typically 15 to 30 kilojoules. Again, you can use a metal organic framework, dope it to make it better. You can start with magnesium, dope it to make it lighter on hydrogen binding. What you require is 15 to 30 kilojoules per mole. Magnesium is very strongly bound, it's 60 kilojoules. Whereas MOF is just 1 to 5 kilojoules per mole. So both of them are not good. So that is where we need, again, doping as a strategy. And in fact, I have come up with one material, which is scandium doped MOF, which I believe is a very good solution for the hydrogen storage problem. But I think we still do not have a good room temperature hydrogen storage material. But if we can get, hydrogen has a lot of applications. As you know, in the fuel cell, a lot of things can be charged with hydrogen, and it will be fantastic. We look at artificial photosynthesis. That's going to be another major challenge in the material science. Again, computational chemistry can play a very important role here. As all of you know, light emitting diodes is a very brilliant example. Silicon by itself is such a poor conductor. As soon as you dope by group 3 and group 5, you give a very good conductor. And today one knows how the LEDs have been used everywhere. You know, watches, digital clocks, television screen, traffic light. It's just amazing. And these, again, can be computationally designed today. All the strategies can be computationally done. And the experimentalists will get a lead. And that is where computational science is going to play a great integrator. In fact, today, when in the COVID time, many research has stopped, One thing that has not stopped is computational science. People continue to do research in computation. All of you know that even COVID virus has been simulated by so many people, so many different angles people are looking at only by simulations. And many papers are coming up. I hope all of you are seeing that in very good journals. So the computational science is going to play a very important role. One of the things that computational science is also going to touch upon is nanomaterials. Many of you, nanomaterials, of course, is very important. I do believe, I don't know how you feel, but I do believe if you ask me, what are the two fundamental science in nanomaterials? I would say discovery of electron microscopy and fullerenes. These are my two texts, which are the major discoveries of nanomaterials. Without electron microscopy, nothing could have been done. In fact, they have got Nobel Prize in electron microscopy from the IBM Zurich, the IBM labs, and all of you know. I end now with just one small topic, 2 minutes it will take me. That is, along with the physics-based computational science, I must say the informatics is also playing a very important role. In fact, today I must say informatics because a lot of data science is using informatics. This is represent a phenomena more of a mathematical, but not in physics-based approach. Informatics has a lot of mathematics, but not necessarily physics. So you have a lot of experience. From there you try to extrapolate by artificial intelligence, machine learning, and so on. So more empirical, but very high throughput. You have problems of rigor. That's a problem. But very often the informatics is going to play a very important role. Today in chemoinformatics, bioinformatics, many of these are going to be used for drug discovery. So it is wrong. It will be actually extremely prudent to accept that the computational chemistry alone cannot do drug discovery. Informatics has to play a very important role. In fact, many companies are hiring people who are expert in informatics. So one of the tools that they use is quantitative structure activity relationship. It's an empirical tool, QSAR. Many drug companies are doing this. But note that the physics behind QSAR is very weak. It's actually mathematics. It's just having some experience, collecting the data, fitting that, and then trying to predict what will happen. So if your data set is good to predict the outcome, then only you'll get good result. So I think that is one of the dangers, but I must say that the computational science must have informatics. It would be unfair for me if I don't tell at least the informatics. I think I will end with these emerging areas. I said it again, synthetic biology is going to become a very important area where the chemist will learn biology, and the way the biology does in nature will try to synthesize in the lab. Biologists also would learn from chemistry. So I think it's a very important area. Many universities are starting synthetic biology in a very big way. I hope most of the institutions will also do. And this would be very innovative ways to carry out research. So I think this is very important, that when we start the new normal, how do you become innovative to carry out research? And that everybody has to start thinking now, as things are unlocking, but things will never be exactly the same. So how do you do that in that period? Well, this is the final slide. I just wanted to say that I could not talk about my work. I just said the metals and doped metals, the hydrogen storage, a little bit about the catalysis. But my main work when I started was actually quantum mechanics. I must say that unfortunately I could spend nothing about that. I am basically an expertise in electronic structure of molecules, many body theories, ab initio quantum mechanics, particularly couple cluster. So I developed lots of theories on couple cluster based methods for molecular properties. In fact, just recently I wrote a review article in Journal of Physical Chemistry. We are also looking at couple cluster for resonance by complex absorbing potential. We are looking at relativistic couple cluster. So many things that we are doing I could not talk of. So I just thought I will show only one slide. I was more interested in the materials part because that's something that can be covered easily in a small time without being too technical. I think with this, I just give some acknowledgement of certain sources from where I took for the education part, particularly chemical education. And with that, I will thank to my colleagues and collaborators and students from NCL, IIT Bombay, IISER Kolkata, my collaborator, Dr. Vidya Osare from SP College, Pune. And of course, I must say hats off to my teachers of chemistry. In fact, at the school level, but a major change took place when I went to IIT Kanpur. We had great teachers. I must say, it's very hard to say how many great teachers IIT Kanpur had during my time. You know, from starting from Professor C.N.R. Rao, Professor Govardhan Mehta, Professor Animesh Chakrabarti, Professor Dev Prabhakara, Professor, D. Balasubramanian. It's amazing. Professor M.V. George, amazing set of chemists who taught me. And on a chemistry teachers meeting, my thoughts go to them, that they have been wonderful. Of course, I came to ISCS Kolkata, and that was a very, very debatable decision, because I did not go abroad from IIT Kanpur, which is the normal thing to do. I somehow did not like to go abroad. I stayed back in India. I joined TIFR, and then from TIFR, actually, after 9 months, I moved to ISCS Kolkata, and it was very hard to justify my move. Nobody does this. And I remember two teachers, Professor Mihir Chaudhary, who actually told me that you are making a mistake. Then I said, I have made many mistakes in life. Maybe many mistakes together will be right. There'll be cancellation of error. And he laughed at, Professor Mihir Chaudhary, those who know, he's no more today a great teacher. And of course, my own PhD supervisor, Professor Devashish Mukherjee, who's also, I learned a lot of quantum chemistry from him. So my thing goes out to many of the teachers that I have been taught. And of course, then I've interacted with several teachers of chemistry. So today on that chemistry teachers, my hats off to all the chemistry teachers. It's a great subject to teach, because chemistry is there everywhere. And that is what I wanted to tell you. Thank you very much.
Thank you, Professor Pal, for speaking on a topic which is so important for all chemistry teachers. Thank you so much, Professor Pal.
Thank you. Thank you. Welcome.
And maybe participants would like to interact with you. We may, I think, spare 5 to 10 minutes, 5 minutes at least.
Yeah, I mean, if you want, because it's already late, so I think the next speaker might be waiting. No, but it's okay. Yeah. Ask me. Yeah.
May I start with a query?
Yeah.
So at the very beginning, you have mentioned that brilliant students nowadays are not attracted towards chemistry. They rather love physics or biology.
Yes.
So is it the failure of the teachers, or chemistry is not an interesting subject?
Yeah. So this is I would not say both. I mean, it's not a failure of the. I mean, I think it is in the nature of chemistry. You have to understand that chemistry is an incremental subject. And my teachers always used to tell me at IIT Kanpur. In fact, other day I was discussing with Professor Govardhan Mehta. He also told me the problem with chemistry is that it's an incremental subject. I hope you understand. So it moves a little bit. You do change, you do another change, and so on. But what is required is a fundamental change that, unfortunately, chemistry is not able to bring in. So that is one of the problems. Whereas in physics, time to time, there's a fundamental understanding. Fundamental, like quantum mechanics, when it came, it completely wiped out our thinking, which was classically driven. And so on. So physics brings in such changes. Biology is, of course, is happening today. With biology are understanding so much. Biology is a natural thing. So I think it is partly natural. And that is the reason many people get worried that even the chemistry Nobel Prizes are going to biology and so on. It's partly natural on the fact that the subject is like that. But I think we have to also look at big problems. What we are missing is a big problem. That is the problem. For example, if somebody can really do nitrogen to ammonia at a scale which is much cheaper, because you know how much of power goes in the Haber process, existing Haber process, I think chemistry will become exciting. If we can really do CO2 to methane, one-stop catalysis, I mean, chemistry would become interesting. So I think the big problems are something which probably are difficult to solve. I'm not blaming the chemist, of course, because it's very difficult to solve. I myself one. So it is happening in an incremental way. So when it happens in an incremental way, we get adjusted. So the excitement level never becomes very high. But if something very significant happens today, I think the excitement goes up. And the students, when they take up subjects, they get excited. Apart from that, I told you that physics and biology are easy to feel at the school level. So it's very important, because physics I see everywhere. Biology also I see. Chemistry you cannot show them in the school level unless they go to laboratory. They don't know what's a reaction, what's a molecule. So I think it is in the nature of the subjects that is happening, but we have to make chemistry interesting. I think that is our job. We should not give up. It's very important.
Okay, Professor Paul, do you think it is an Indian scenario or it is a global scenario?
It's a global scenario. I talked about even the Nobel Prizes, right?
Yeah.
So it's a global scenario, of course, that the chemistry is by definition, not by definition, chemistry has become an incremental science. I would not say by definition, that's not to say.
So it's
But
a
I think we have
challenge
to,
for the chemistry teachers.
it is a challenge. So, but once in a while, of course, very big discoveries come up, even in chemistry.
Yes.
That will give the boost to the chemistry. So catalysis, I find there's one option, catalysis. Polymer, when it happened, because it has such a societal applications, the polymer became very exciting. So I think once in a while this is bound to happen, but we have to see that it happens more times, and at least even if it happens or not, we have to excite the students. That is where the opportunities lie.
Okay, thank you so much. Or any participants have some query to Professor Paul?
I see in the chat box if there are any questions. You roll up. Yeah, transdisciplinary. Somebody has talked of transdisciplinary, which is very important. And I think it's very, very important point. So in case there is somebody who wants to ask, you can unmute the person, then that's better. You can raise hands. Somebody has written, I mean, these are all comments. It's instructive, etc. These are mostly comments. If you find any question, please let me know if you are checking this. Please, yeah. One new message. Okay, it's the same. Yeah. Challenge of chemistry compared to physics, maths, and biology. Yeah, I think that is a very important part, the hierarchy of science. And I think we have to understand where chemistry comes in the hierarchy of science. Yeah. Thank you.
Professor
Yeah, thank you.
Paul,
Thank you very much.
I think next speaker is waiting.
Yeah, I think so. I am sure.
Conclude here. We thanks a lot, Professor Paul, for accepting our invitation from NCCT and giving such an excellent presentation. Thank you, Professor Paul.
Thank you.
With this, I thank both the speakers, Professor Venkata Narayan and Professor Saurabh Pal, for presenting their lectures in this technical session, which I shared. I thank both the speakers, and also I thank Professor Convener, Professor PM Mishra, for inviting me to share this technical session. I think next two lectures should be shared by Dr. Helen Kobita. I hand over to her. Thank you all. Thanks all.
Thank you, sir. Thank you, sir. Thank you, sir, for your wonderful presentation. You have so many things, sir. Please accept.
Thank you. Welcome.
Thank you, sir.
Welcome. Yeah. Thank you.
Thank you, Professor Dekha, sir, for your precious time. May I now request Professor Helen Kavita, Madam. She is the Professor and Head, Department of Chemistry, SRM Institute of Science and Technology. She is also the Vice President of ACT South Zone, to chair this particular session. Over to you, Helen, Madam.
Thank you, Dr. Amit. Very good afternoon to all of you. I'm very happy to be the session chair for this technical session. At the outset, I thank Professor Premohan Mishra sir and our General Secretary for giving me this opportunity to share this session in this prestigious NCCT. First session of this technical session will be given by Dr. S. Shivaraman. I'm happy to introduce a very eminent scientist who is going to enlighten us now. Dr. Swaminathan Shivaraman is a polymer chemist by profession and a mentor as well as science administrator of distinction. He is the former director of CSIR, National Chemistry Laboratory, Pune, Shanti Swarup Bhatnagar Fellow of CSIR, and J.C. Bose Fellow of Department of Science and Technology. Currently, he is an honorary professor and INSA Senior Scientist of the Indian Institute of Science Education and Research, IISER, Pune. Dr. Shivaraman is a highly decorated scientist, born technologist with numerous awards and honors to his credit. He was conferred Padma Shri by President of India in 2006. He is a recipient of the Gold Medal of the Chemical Research Society of India for his lifetime achievements in chemistry in the year 2019 and the International Award for Distinguished Contributions to Polymer Science awarded by the Society of Polymer Science, Japan in the year 2017. Dr. Shivaraman earned his Bachelor of Science degree in chemistry from Madras Christian College in the year 1965, and he is a distinguished alumnus of IIT Kanpur. He has done his MSc in 1967. He earned a PhD in chemistry and DSc from Purdue University, Indiana, USA. He is an elected fellow of all the learned academics of science and engineering in India. He is a technical consultant to several reputed Indian companies and serves on the board of directors of several leading Indian companies dealing with chemicals and materials. Dr. Shivaraman's research interest concerns polymer synthesis, surface chemistry of polymers, porous polymers for energy-related applications, biodegradable polymers, organic-inorganic hybrids, nanocomposites, and structure property relationship in polymers. He has authored over 245 papers in peer-reviewed journals, edited 2 books, and authored 1 book. He is cited as an inventor in 51 issued US and European patents and 52 Indian patents. He has supervised the doctoral thesis of about 40 students and mentored over 15 postdoctoral fellows in a research carrying span of 50 years. We are very much privileged to have such an eminent scientist with us today. I welcome you, sir, on behalf of the organizers. Over to Dr. S. Shivaraman, sir.
Can you hear me?
Yeah, sir. Yeah.
Thank you.
Welcome you, sir.
I'm just going to share my presentation. Just give me a few minutes.
Yeah.
Can you see my presentation on the screen?
Yes, sir.
Yes, sir.
Thank you. Thank you very much. A very good afternoon to everyone. I'd like to thank Dr. Helen Kavita, the chairperson of this session, for that generous introduction. The conveners of this National Convention, Professor Mishra, Professor Prabhu, who invited me to share my perspectives at this event. Ladies and gentlemen, I'm not going to talk about my research today. I thought I will talk about something related to chemistry and its education. In fact, my friend and former colleague, Saurav Paul, has made my job very easy because he has probably echoed several of the thoughts that you will find in my presentation, but maybe in little different words. So I think the background that he has set has been extremely useful, and therefore it will be easier for me to communicate very quickly what I have in mind. Since there is a little bit of difficulties in managing a discussion forum in such kind of web seminars, I have given my email here. Please make a note of it. Those of you who are listening to me, please make a note of my email. And in case you wish to receive a copy of my presentation or you wish to ask me any question, you may just send me an email, okay? And I will try and respond to you in the best manner I can, because that could be a much simpler way of handling our interaction. Of course, I will be available for any questions at the end of my talk, but please make a note of my email. And those of you who would like a copy of this presentation, please send me an email and I will send you a copy. Thank you very much for your patient listening. I think what I'm going to talk about today is a little bit of what chemistry is all about today. Okay. And how do we therefore teach this chemistry to students who wish to learn chemistry? And what are the challenges that we have in the process? And therefore, how do we make a decent job of our job as teachers? Well, what is chemistry? I think all of us know what chemistry is, but I just want to kind of highlight my understanding of what is chemistry. We all know that chemistry is the science of atoms, molecules, structures, matter, so on and so forth. But two things I want to focus on chemistry, and Saurav may not agree with it completely, but chemistry continues to be primarily an intuitive science. And I think this we must understand that chemistry is powered by human imagination more than any other faculty. The second is chemistry is uniquely utilitarian. And in fact, this is one of the reasons why when Saurav said that young students do not really like chemistry, is because when something becomes very utilitarian, it becomes mundane. And that's one of the reasons why chemistry has lost its sheen. The reason chemistry is utilitarian is we find chemistry in applications all around us. And that means that this chemistry that people have done in the past have led to a lot of materials, a lot of pharmaceutical drugs, colors, a variety of things, textiles, everything that we consume today, and everything is based on chemistry. I will not get into the details of this because I think we had a great lecture by Professor Angela Wilson a few days ago, which I had a pleasure to listen. And I think she very succinctly exemplified the role of chemistry in the world in which we live in today. And I think that is, much of it is driven by a high degree of utility. And that is something that we cannot escape when we talk about chemistry. Well, this is exactly what people taught us close to almost 100 and 240 years ago. And basically chemistry creates its own object. The creative power of chemistry is actually in the process by which it creates objects. Objects could be molecules, structures, supramolecules, hierarchical structures, variety of other things that chemistry can create. And that is what I think Marcelin Berthelot, who is considered to be the first chemist of the world in a sense, or at least the first organic chemist of the world in a sense, taught us. And he said that chemistry is distinguished by the fact that it can create an object. And that is very unique to chemistry, because please understand that physics and of course biology is recently creating objects using the principles of chemistry. But otherwise, conventional biology and conventional physics actually only study existing matter. And I think it was only chemistry which created matter. And that's the unique feature of chemistry. And in fact, I quote here below a very perceptive statement by Richard Feynman, who said that what I cannot create, I cannot understand. And that is something that many of you may want to think about a little bit more, because this is a deeply philosophical statement. What I cannot create, I cannot understand. And this is what Richard Feynman told to us long years ago. Well, what is the structure of chemistry that we're talking about today? It's laws, axioms, theory, concepts, and principles. Chemistry is actually in 3 dimensions. In fact, this is something that our students are not, in opinion, taught very well, because we teach chemistry in 2 dimensions. Very often the students don't appreciate that chemistry has a spatial dimension. It has got a spatial feature which is extremely important in chemistry. And in fact, we do a very poor job of communicating it, because of the fact that we tend to, even today, in spite of the fact that we have enormous amount of tools at our disposal, we still continue to teach chemistry in 2 dimensions, which is a sad story. Visualization is extremely important, especially in temporal dimensions. And in fact, again, chemistry has to be visualized. I mean, we don't teach this at all in our institutions, how to visualize chemistry and how can we actually understand molecular motions, how can we understand collisions, how can we understand bond making and bond breaking processes, which is all can be done through very deep visualizations today. And this is something that is not part of the teaching pedagogy at this moment. And lastly, of course, chemistry is the relationship of structure to properties and ultimately to functions. Origin of colors, smell, taste. Why does sugar taste sweet and salt taste salty? What's the difference in terms of chemical structure? And why does it taste differently? Is a question which is fundamental to chemistry, but most students of chemistry will find it difficult to answer. Sensation, tactile sensation, physical properties, biological response. These are things that enable us to relate the structure of a molecule to its final properties. In fact, we should remember today, as when you're talking about chemistry, Linus Pauling, I'm sure many of you know who he is, a very famous book that he wrote. It's a Bible for chemists. He built bridges in chemistry. And in fact, that's why I remember him today, because he was the first one to show that physics, chemistry, and biology can be integrated. And in fact, this was a monumental contribution of his time in the 1930s, because many believed that physics, chemistry, and biology were 3 distinct disciplines, unconnected. And it was Linus Pauling who taught us that physics, chemistry, and biology can be bridged through knowledge, which we today understand as chemical physics, physical chemistry, biochemistry, chemical biology, so on and so forth. And I think he also created, like what Sauropol talked about, the entire field of quantum chemistry, the computational aspects, which is today the most powerful tools in the hands of the chemist. And that was again created, taught to us by Linus Pauling. So I think we must, since we're going to be talking about a little bit of knowledge integration today, I thought I should highlight his contribution. I think this is something that we must remember. It was done almost 100 years ago, but I think it is worth remembering today. Well, chemists make molecules. Most of the chemists make molecules, whether it is inorganic, organic, biological, they all make molecules. Polymers, they all make molecules, and that's why it's a creative science. And I think the chemistry, the synthesis is a defining character of chemistry. That the fact that chemists can take atoms and assemble them into molecules. And that is what makes the chemist a very unique species amongst the scientists, of various natural sciences disciplines. I'll give you an example. I think this is all, we know this very well, but I just thought I'll highlight this. 1828, it was a landmark year, an event when we had the synthesis of urea. Urea is a very simple molecule, right? NH2C double bond O NH2. But look at this. By 1972, we had Robert Woodward, who was able to make vitamin B12 in the laboratory. Okay, enormous skills and chemistry that was needed to build this molecule. Well, 1972 looks now very far away, but look at this. There was a gentleman called Hisey at Harvard University who in 1989 made a molecule called polytoxin. And polytoxin, look at this, it's a molecular weight of 2,675. Compare that to urea, which is such a simple molecule discovered in 1828. 64 chiral centers, 7 double bonds exhibiting geometrical isomerism. And I think it is considered to be the Mount Everest of organic synthesis. An amazing synthetic feat created in the laboratory. Look at the ability of chemists to assemble molecules from constituent atoms. Now, We believe that chemical synthesis, which has evolved over close to 200 years, has actually reached a level of perfection beyond which it's probably very difficult to reach. And I think we have reached almost the perfect levels of what is called an ability to put together atoms and make molecules. But then I think Saurav Paul mentioned this in his talk. Molecules are just no longer important. Once upon a time, to make a molecule was considered to be one of the main objectives of a chemist. But today, molecules are not important. Systems have become more important, and I'll talk about this in a little while later. Because everything that we talk about today are no longer just molecule; it is a system that we are talking about. And lastly, structure is no longer important. Structure today. An average chemist with available tools that is available to him in his laboratory can determine the structure of anything under the sun. There is no problem. Okay, structure is something that is no longer a great challenge, at least for chemical molecules. But today we are more focused on functions, and therefore, what chemists tend to ask today, and I think this is what we must learn. We must learn to teach the students is not what is it. Most of the time earlier, we were asking, what is it? What is this molecule? What is this property? But today, we are asking the question, not what is it? We know what is it. The question is, what does it do? Is a question that we ask. And that is a question that is most difficult to answer for chemists, because the kind of knowledge that we have still today is unable to give us this complete understanding of what does something do in that space that we are looking at. And therefore, look at this. This is what I call the future of chemistry. We talk about hierarchical and multi-scale structures. We talk about hybrid materials today. No longer organic, inorganic, biological. It is a combination of all the things that we talk about today. Microphases and morphology, interfaces and molecular junctions, multiple molecules cooperatively defining response and functions. The question is, how do we relate the basic understanding of chemistry to all these kinds of structures that we actually encounter in real world? And therefore, and that's what leads to a whole lot of what is called processes: electrochemistry, catalysis, polymerization, ion diffusion and transport, donor acceptor systems, oxygen reduction, porous material, conducting materials. A whole lot of such processes have now emerged in order to create these so-called functions in molecules. Well, I look at 3 dimensions of chemistry as being very important. I call it the science of materials, the science of sustainability, and the science of life and nature. To me, chemistry implies to me that through chemistry, I'm going to address these 3 scientific problems in these areas. Using chemistry, using the knowledge of laws and knowledge of chemistry, I'm going to be able to understand the science of materials, the science of sustainability, and the science of life and nature. Well, I will not get into the details of these things. This is, if you look at any current advanced material, you will see it's a hybrid of material. There are organic compounds, there are inorganic compounds, there are carbon materials. A whole lot of materials are actually assembled together in order to create a function. Now, no single component of this family will give you the desired function. And that's why I said these are complex materials that give you the kind of function that you're looking for. This is just an example of what is called an organic photovoltaic, a film that can actually harvest solar energy. And you just want to just look at the structure of this film. You know, it has organic compounds, it has inorganic materials, it has metals, it has oxides, a variety of things that are assembled with a purpose. The reason it's assembled is because each one of them deliver a function, and together they create the utility of this material. And this complexity of materials is what we have to understand as chemists today. And similarly, you take a fuel cell or you take a lithium ion battery, which is something that is functioning in every one of your mobile phones, and look at the complexity of material that has been assembled together in order to create the function, whether it is generating energy or it is storing energy. Both of them are based on, in my opinion, exquisite applications, the principles of chemistry. But I think this is what I believe that young men and women must appreciate when they learn chemistry. Well, chemistry is also key to the sustainable world in which we want to live, in which our children would like to live. And what is chemistry? Chemistry is nothing but matter flows from the ecosphere to the human economy, because we chemists are masters in extracting matter from the environment and then using it in the human economy, whether it is minerals, whether it is organic compounds, whether it is inorganic compounds. All of them are extracted from nature in one way or the other. And then what do? We consume them, we use them, and we discard them. And the matter flows from human economy back to the ecosphere. But as of today, this happens in a linear fashion. There is no closing of the cycle. The matter is taken away from the environment and then flows into a waste stream. And this is what is creating the entire problem of sustainability. And I think as chemists, we have to understand this economy, ecosphere, material flows. And this is again driven by thermodynamics, driven by entropy, driven by enthalpy, driven by chemical kinetics. And I think these are the principles of chemistry that will dictate our ability to tackle this complex problem of sustainability. Now, if you look at this, I always say this, nature has designed this universe in the form of cycles, where everything is returned back to nature after their use. But humans have designed the processes and technology in a linear fashion. It does not get back to the nature again. And that is why one of the major issues of learning chemistry today is to understand how to close the cycles. Whether it's the carbon dioxide cycle, whether it's the hydrogen cycle, whether it's the carbon cycle, whether it's the nitrogen cycle, the phosphorus cycle, the fuel cycle, the ocean pH cycle. How do we control these cycles? How do we make them truly cyclical? And that is very critical to understand issues of sustainability. And understanding issues of sustainability, in opinion, is going to be one of the core responsibilities of chemistry and students of chemistry. And the question basically is, how much of the chemistry, how much of the kinetics, thermodynamics, enthalpy, free energy, everything that they learn, are they able to relate to these kinds of cycles? And therefore, I don't get into the detail. In fact, I give a course on this. I teach these cycles to students of chemistry. And I think it is something, there are many cycles we teach them using the principles of kinetics, thermodynamics, enthalpy, and entropy. We teach these cycles to students and ask them, how do we learn to close these cycles? Because to me, that is the key issue in sustainability. Well, that has led to this entire understanding of a discipline now called circular chemistry. And I give you a reference. If people want to go and read them more, it's a concept of circular chemistry. And the circular chemistry is beyond green chemistry. In my opinion, it is something builds on green chemistry, but it's beyond green chemistry. And the question of circular chemistry is, how do we close these circles, these cycles? And ultimately, circular chemistry is believed to will lead to circular economy. And that's the way society will see the impact of chemistry in our environment. So the circular chemistry is actually a predecessor to building what is called a circular economy. Well, if you want to build such understanding of circular chemistry, circular economy, we simply cannot use a reductionist approach. And in fact, one of the problems with chemistry is chemistry has been predominantly reductionist in its philosophy. We always thought that all we have to do is understand atoms, the electronic structure of atoms, and that's good enough for us, because then we can do everything in chemistry. Unfortunately, no. Understanding atoms is important, understanding molecules is important, but there is a world beyond atoms and molecule that is even more important. And that is something that we need to communicate to our young chemists who are learning chemistry today. Again, if those of you are interested, there are very deep analysis of this topic in the literature today, and that is, how do I build in systems thinking in the minds of students of chemistry? And I think that is very important, because we must learn to think of this world as a system and not as atoms and molecules. Because only when we learn to think of this world as a system that we will come up with the right solutions to the problems that are facing this world. And I think this is, again, something that we must impart this education, in the classroom, in the various ways of experiential learning to students who are learning chemistry today. Well, I will come to a few minutes of what I call the challenges in teaching the chemistry, because that's where the problem is. And I think, pardon me, I think I'm speaking to a lot of teachers who are very dedicated teachers. I have no complaints. I think they're all doing extraordinary work. But I want to say that teaching as an institution in our institutions is archaic. Most of our institution teaching has become very, very pedestrian. And I think we must recognize this, otherwise we will not change. It is non-demanding. It is lacks innovation and experimentation. It is rigid pedagogy. Nothing flexible about it today. And I don't think it meets the needs of what I call the millennial generation. The millennial generation are the people who are born after 2000. Unfortunately, most of us teachers are born much earlier, and that's where the problem comes. And I think our education in chemistry does not make our students future ready. And I think that is what we have. It is not important for them to be, to be ready today. They have to be useful 25 years from today in this world. And that is the challenge of teaching. And I think that's where I think we are largely failing in our teaching of chemistry. Well, the first thing, my problem, and I think Sauropal has already talked about it, I think we must dispense away these artificial barriers which we have created long years ago, and we have no courage to leave them. And I think Sauropal touched upon this. There is no difference between physical, organic, inorganic chemistry. Even then, today, in major institutions, there are different buildings for inorganic chemistry, Department of Inorganic Chemistry, Department of Physical Chemistry, Department of Organic Chemistry. Even in some of the most premier institutions of India, we have 3 different buildings for 3 different departments of chemistry, which is very sad. Because to me, in fact, this we have experimented in an institution recently in the last 1 year. All chemistry should be taught only, not as inorganic chemistry, organic chemistry, and physical chemistry, but in terms of structure, dynamics, and functions. And I think that's the only way to teach chemistry. And I think we have just experimented for a year teaching chemistry, at least to the master's degree student, using structure, dynamics, and function as the key parameters of teaching chemistry. Well, if you use structure, dynamics, and function, we also naturally integrate chemistry and biology. And this has been one of the biggest problems, because chemistry has been looked at different from biology. And I think this is a sad story again, because chemistry and biology are not different as long as you look at structure, dynamics, and functions. In fact, the recent depth of studies that are coming in the newspaper on how COVID-19 infects a human ACE2 receptor in our lungs is a classic example of structure, dynamics, and function, which I think chemists will easily understand and appreciate. But actually, it's a biological reaction. But I think we must learn to cast the entire discipline of knowledge that we are teaching in the form of structure, dynamics, and function, and leave the traditional boundaries away, move away from traditional boundaries. And I think this is going to be very important if we have to make our students what I call future ready. In fact, I call biology and chemistry as 2 sides of the same coin. I don't know why we are making such a big fuss about Department of Biology being different from the departments of chemistry. In fact, most chemists, after their PhDs, will end up working in biology today. 50% of the chemists will end up working in biology, 50% of the chemists will end up working in material science. Okay, there is no other chemistry today. Everybody will be working in biology in some way or the other. And therefore, structure, dynamics, and function constitute, in my opinion, the central theme of chemistry. And I think this must be the framework in which all chemistry must be taught. And I think if we don't do this, we are not doing justice to the students in the future. In fact, Saurav Paul pointed this out, and I want to highlight this again. You look at the last 5 years of Nobel Prize winners, okay, in chemistry. And I asked the question, how many of our chemistry students can explain to me the work of these Nobel Prize winners? Okay. And I sadly so, I have tried this with students of chemistry who are master students of chemistry, and very few people can even understand the language. Forget about understanding. No, people don't know what is an antibody. They can't explain to me what is a phage, you know. They don't know what is genome editing. Now, these are the people who are winning the Nobel Prizes in chemistry. And that's where the disconnect today in education lies. Most master students cannot answer these questions today, which is very sad, because Nobel Prize in chemistry is considered to be the singular biggest honor that a scientist can ever receive. And the students of chemistry cannot explain why these people got the Nobel Prize for chemistry in these subjects. And that means they haven't understood that there's a chemistry behind all of them. And if we don't understand there's a chemistry behind all of them, we think that, you know, some biologist is getting a Nobel Prize in chemistry. It's not true. Jennifer Doudna was trained as a physical chemist. Okay, Francis Arnold was trained as a chemical engineer. Okay, all right, and and G. Winter was trained as a biochemist. So all these people were trained in chemistry, but they are working in areas of deep biology. And that is what I think we must understand, that is what we have to learn to teach in the curriculum, so that they at least a student must be able to appreciate the science behind the Nobel Prize winners, which I think very often they do not even know, they don't even understand. I always say this, and Hoffman said this long years ago. I don't think nobody can ever say this better than Roald Hoffman. I think we all know who he is. Disciplines are human constructions, the conservative compartmentalizing affliction of academia. He calls it an affliction of academia. And I think we must admit that we are all afflicted by a disease in which we believe that our discipline is very important. And these are narrow disciplines without understanding that it is not, our discipline will not survive without other disciplines around us. And therefore, we must kind of learn to break these kinds of barriers between disciplines, which I think Saurav also very eloquently talked about. Well, Saurav has already talked about this, and I will quickly run through this. I think we all know what physics, chemistry, and biology is all about. I don't want to spend time. We always say that essentially chemistry deals with non-living matter, and biology deals with living matter. So both of them are dealing with organization of matter. So what is the difference? In my opinion, there is no difference. I think that's the way we need to appreciate that chemistry and biology are no different, especially molecular biology is no different. Now, in fact, this was Arthur Kornberg. Again, he was a chemist, by the way, okay? He did this, he got a Nobel Prize in chemistry in 1959, a very well-known man. Both father and son won the Nobel Prize. One of the rare occasions where a father and son both win the Nobel Prize. His son is currently a professor at Stanford. And what I think Kornberg told us way back in 1987, that it's a language of chemistry that bridges the physical world with the biological world. And I think that is the link that we have to communicate when we teach chemistry, okay? That we are connecting the physical world to the biological world. And of course, his famous paper that is one of the very well cited publication of his, apart from his Nobel Prize winning work, is, of course, is called the two cultures the chemistry and biology, which is, even if you read today, it makes sense. Well, in fact, this is why if you ask today a student of chemistry, an average student of chemistry in a college, can he understand the difference between a virus and a bacteria? Does he know what is an antigen and an antibody? Does he know what is the difference between a DNA and an RNA? Or what is the difference between a vaccine based on live attenuated organisms or a messenger RNA? These are something that you're reading in the newspaper every day today, am I right? But most chemistry students will not be able to understand any of these languages, which is very sad. You know, ask us chemistry students, what's the difference between a virus and a bacteria? Okay. What is the difference? How does a bacterial infection work? What does a viral infection work? And today we are in the midst of a COVID-19 viral infection. Most students of chemistry will find it difficult to give precise answers, which is very sad, because this is what I call common knowledge today. And I think when I have graduated in chemistry and I can't answer this question, that means maybe I haven't learned the chemistry that I need to learn. Well, chemistry is now becoming what I call, in fact, I talked about complex matter. It's complexity which is becoming very important. And what is biology is already was complex, you know, it's what's called emergent properties. And I think, therefore, today, and I alluded to in my earlier slide, systems chemistry is all becoming very important. How do I understand a new discipline which is called systems chemistry? I talked about circular chemistry earlier. Now I'm talking about systems chemistry. What do we understand about emergent properties in matter? Because if you understand emergent properties in matter through chemistry, we are able to come a little closer to understanding the living matter in biology. And that is the challenge of chemistry today. And actually, complexity in chemistry is what is all about, is one of the frontier areas of science today in chemistry. And essentially, life is the ultimate showcase of what complex chemical systems can create. Ultimately, what is life? It's nothing but chemistry, but it's complex chemistry. It's no longer a simple chemistry that we learn in a textbook. The question basically is, how do we learn to appreciate the complexity angle in chemistry? And this is going to be a very important part, because this is a new stream of thought that we must all get in order to connect the simple molecular understanding of matter provided by chemistry with the complex emergent behavior of biological systems. And this is called systems chemistry today. Okay, systems chemistry is something that integrates many disciplines of chemistry, okay, and leads to systems that can self-assemble, produce and consume energy, process information, manufacture materials, replicate, self-heal, a variety of things that nature does. We can actually do it in man-made materials. And that is because we understand the concept of systems chemistry. Well, no wonder that when Kronberg said that principles of chemistry connect the physical and biological world, it was John Mary Lane who gave us a little extra knowledge about this in terms of what these are. And this, he called it the supramolecular science and the principles of molecular recognition and self-organization. And this is something that is intrinsic to chemistry today. Very, very few students learn about these things in chemistry today, at least the principles of this, but unfortunately, this is something they must learn, at least the core principles of this, because this enables them to understand and appreciate the complexity of chemistry. And therefore, Saurabh Paul again talked about hierarchy of science. I just want to exemplify that in a different way. You know, we are talking about a physical world, which is physics and mathematics, inanimate world, which is chemistry, and a living world, which is biology. And the question is, how do inanimate matter become a living matter? This is one of the most fundamental questions that scientists are asking today. And again, how do we connect everything to the human world? Because even biology, which is a living world, is not a human world, you know. And how do we connect that? And how do we blur the boundaries between the physical, chemical, biological, and the digital world? Because when it comes to this, you have to use a lot of digital tools to appreciate. And how do we therefore kind of erase these boundaries between these worlds? And therefore, the question is asked, we are in the biological world, we seem to understand in great depth about many things of the biological mechanisms in our systems, but how do we connect to the human world? And I think this is a question which is begging for answer today. And I think ultimately, in opinion, understanding science is to relate the physical world to the human world through chemistry and biology. And I think that is the ultimate goal of science. And I think that is what I believe should be the understanding that chemistry must get. A chemist must get that in this chain, he has a very critical role to play. Well, so that's the question. And because you can see that I understand everything about the gene, I understand everything about a protein, about the cell, but still I don't understand the human being. And that's the missing knowledge that we still have. And again, chemistry is going to be extremely important in this journey. Well, so what is the challenge of teaching? I'll take a few more minutes, convey the flavor of what I call the interdisciplinary flavor, and I call unity of science. I think to me, all science are the same. It's the unity. You may be a little bit more of an expert in one than the other, but I think we must appreciate the beauty which lies in the unity of science. And I think we must tell young minds and young people that science is a unitary discipline. Science is not a fragmented discipline. It is a unitary discipline. We must teach students to differentiate between concepts and facts. Most students learn facts, very few learn concepts. Facts they will learn today, they will forget tomorrow. And concepts they don't learn, and therefore they don't understand. Information and knowledge. Again, a lot of information that they will learn today, but they can forget tomorrow. Information has no long-term relevance, but knowledge has a long-term relevance. How do we differentiate between these? Engineering and science, again, we have made, without engineering, science has no role. And I think that is something that we must at least convey the flavor of that. I'm not saying that you must teach engineering to students of science, but at least they should know that engineering is critical to science. And of course, exemplify with examples the structure to function journey. And I think that is a kind of a case study which will exemplify all principles of chemistry, from bonding to electronic structure to material properties to its applications. And I think that's a beautiful way to teach chemistry, from structure to functions. And I think the question basically is, are our academic departments as presently structured capable of meeting these challenges? And I have my grave reservations on this, but I think this is something that we must all think about. Well, 65% of our children entering school today will have a job that does not exist today. Please understand that. 65% of the children who are entering the school today will have a job maybe 30 years from today that does not exist today. So how do we prepare them for the future? This is the challenge of teaching. Now, people say make them job ready, but what is the job for which we have to make them ready? We don't even know what the job is all about today. We don't have an idea of what the job is all about, because the jobs that are available today will disappear in another 10 to 15 years. And that is a challenge that we have to face. And in fact, Toffler, a great man, a visionary, and many of you must have read many of his books, said that unless we understand the future for which we are preparing, we may do tragic damage to those whom we teach. And I think the tragedy that we are witnessing today. A lot of people are coming out of universities unable to cope up with the demands of an employment even today, because these people were educated 10 years ago. And the challenge is going to be even more difficult in the future because the world is changing so rapidly. I will skip this. I don't have the time to talk about it. What I call the 3 pillars of 21st century skills. You have to look at foundational literacies, and I think to some extent the new education policy has talked about this. We have to talk about competencies and we have to talk about character. And I think these 3 put together is what will make a good citizen. And I think this is something that I will not spend time today. And what is the objective of teaching in educating chemistry? Do we want to teach students what we know? Because what we know as teachers may not be important for them in the future. Or do we want to teach them how to think? And I think this is a fundamental difference. And therefore, I list here a variety of things that we need to bring into a pedagogy of teaching. Okay. And I think unless we do this, we are continuously teaching what we know, because we have learned it 20 years ago and we are teaching them to our students today. Is that relevant to them for the future? I'm not sure. And I think we need to move away from this kind of a teaching to something more innovative. Well, I think this somebody has already talked about. Especially chemistry is not just learning from a textbook, especially in a textbook which is 2-dimensional. I always say chemistry textbooks are actually very, very damaging to learning chemistry because it talks about chemistry in 2 dimensions. How do you understand a molecule like DNA in 2 dimensions? Impossible. Okay. And therefore, I think forget about textbook. You have to learn to use variety of other tools to teach chemistry, including what I call visualization, and we must also be enable them to do chemistry. And I think this is the challenge, because most universities today are short of resources to have good laboratories. And therefore, there is a problem. How do we therefore make them do chemistry, which is do relevant chemistry, not just some archaic experiments, but do some relevant chemistry? Well, all these things will have to be looked at. We must move away from teaching a syllabus, teach to test, teach, and to a concept called teach to learn, from factual to analytical. Fill the mind with facts to open the mind with empty spaces. I think we need to open their mind, not fill their mind. Unfortunately, our education, and right from school days to even university days, is actually trying to fill people's mind, which I think we should leave them. We should actually create open spaces in the minds of the people, because they will think then on their own, from teacher-centric to student-centric. And I think we should not look at education as a mere transfer of what I call explicit knowledge. And I think this is the wrong way to look at education. Transfer of explicit knowledge should be about 25% of the time, but 75% of the time, or 70% of the time, it must be what is called trying to relate that science to the life around them, And I think that is the way I believe that science will become even interesting to young people. Well, we have talked about it, and I think Angela Wilson also talked about it. Saurabh Paul alluded it. How do we integrate a chalk and board with a virtual screen? How do we integrate a physical laboratory with a virtual laboratory? And how do we integrate teachers' content with web-based content? And I think all these things are going to be very important challenges for teachers as we move in the next few decades. And I think this is something that I think we've all seen this. This is what a good classroom today would look like in ICER or something like that. If you go, a good classroom would look like this, which is an undergraduate classroom to teach students of chemistry at the undergraduate level. But now we can see we're already using all these tools, and then a lot of web-based tools will have to be integrated with this. And I think we are all familiar with all these things. And lastly, an amazing amount of actually doing experiments on the virtual space are coming up. Lab Exchange from Harvard University, PHET from the University of Colorado at Boulder. Okay, these are actually the Lab4U is actually you can run experiment on your mobile phone. Okay, chemical experiments you can run on your mobile phone. And these are the kind of platforms that are available so that you can actually integrate physical laboratory with a virtual laboratory. And I think this is going to be extremely important, because how do I run experiments which they can actually visualize, on a screen? And maybe if you have a 3D camera, you can do it in a 3D fashion. By the way, there are visualizing systems which I can now see it in a 3-dimensional fashion. For example, how does an enzyme dock into the protein? I can actually see it in a 3D, in a 3-dimensional way. And I think these are powerful tools to teach. And I think these are, by the way, these costs are coming down. They are not so expensive anymore. Once, about 10 years ago, they were expensive, but today these costs are spiraling down. Okay, and I think people must explore these options. And lastly, and I think this is my last couple of slides, education must cultivate many other things: curiosity, observation, ability to ask simple stupid questions, puzzles in the problems. I think we must understand what is the difference between a puzzle and a problem. Most of us teach in our universities puzzles for which there is a correct answers. In real life, we face problems for which there are no correct answers. And ultimately, I call it the whole brain thinking. I think we need to cultivate both the right brain and the left brain thinking amongst our young people. And lastly, I think collaboration. I think, in my opinion, more and more students must learn to work in teams. And I think the concept of shared science today is very relevant. Science is no longer an individual endeavor; it is a shared endeavor. And I think this we must cultivate in our systems. And I think the epistemology of science, which I think Saurabh Paul talked about a little bit, is something which is missing in our education of science, especially of all students of science. I think epistemology must be brought into the focus, because epistemology is what eventually enables us to understand where we came from, where are we, and where are we heading to, and ultimately how does all these things relate to the world in which we live in and the society in which we live in. And I think that is all taught to us by the epistemology. And I think we miss this. In fact, most students of science will not be able to explain to me what epistemology is, which is sad, because that's what they should know to some extent. And lastly, I just want to conclude this with a very powerful statement, because we all hear today that our institutions don't have resources, our institutions are decaying, our institutions are not being, government is not helping us support them. Okay, we hear lots of complaint where we say everything, the problem lies outside of us. Okay, I just want to conclude this lecture with this powerful statement by Lawrence Lovell, who was the president of Harvard University. And he said, institutions rarely are killed. They meet their own end by suicide. And I think most institutions die not because somebody kills them, a government or an external body. They meet their own end by suicide. They die because they have outlived their usefulness or failed to do the work that the society wants done. I have a strong feeling that if our institutions have to survive and thrive as true torchbearers of creating the talent for the future of this country, we must understand what our stakeholders want. Our society wants, what our students want. And how do we craft our institutions to meet those needs of students and stakeholders? And I think that will only ensure that our institutions will survive. Otherwise, they'll anyway die. So I hope that we don't look at institutions decaying because of external forces. Institutions decay because they internally collapse. And that's the message that I think Lawrence Lovell gave us quite some time ago. And I think his words ring true even today. So thank you very much for your kind attention. I wish to stop here. I think I've said, please use my email. You want a copy of my presentation, I can share with you. If you want some questions, I will answer you on email or any other medium. I think I have also given my, if you go to my website, you will see my mobile number, everything, WhatsApp, everything is there. So please use it if you think that there is something interesting that we can have a conversation about. Thank you very much.
Sure.
Thank you so much, sir. Thank you so much for enlightening us on a excellent presentation on future of chemistry. Thank you so much, sir. Participants, you can just mail Professor Shivaraman, sir, if you have any queries. And we are also running short of time, and we have another speaker with us, Professor Ponnudurai Ramasamy. So I am happy to introduce Professor Ponnudurai Ramasamy, sir. Professor Ponnudurai Ramasamy has completed his PhD in physical chemistry from University of Delhi in the year 1996. And he started his career as a lecturer in chemistry in University of Mauritius in 1997 and worked in several capacities and elevated as a professor and personal chair in computational chemistry group in the same university in the year 2012. Professor Ramasamy is a visiting professor in University of Johannesburg and King Saudi University. He is also a professor extraordinarius, University of South Africa. Dr. Ramasamy has guided 60 undergraduate projects, 10 postgraduate projects, and 12 MPhil and PhD candidates. Dr. Ramasamy has published 7 book chapters. Dr. Ramasamy has published more than 220 research articles on peer-reviewed journals. He has successfully completed more than 1,000 projects worth of 1 crore rupees. Dr. Ramasamy is one of the editors of the Journal of Open Chemistry published by De Gruyter, and he participated and gave keynote lectures in many national and international conferences. Dr. Ramasamy is the external moderator, physical chemistry, for the Department of Chemistry and Biochemistry of the University of Nandia. And also he has examined more than 50 PhD theses. I am very happy and honored to welcome Professor Ponnudurai Ramasamy from University of Mauritius. We welcome you, sir, on behalf of the organizers of this NCCT. Over to Professor Ponnudurai Ramasamy.
Thank you very much, Professor Helen. So can you hear me? Can you, is everything okay?
Yeah. You're
Good.
audible.
So I think, so you'll have to make me the co-host to share the screen.
Yeah, one second.
Sir, you have co-host rights. You can share your screen.
Okay, that's very good. So I will try to share the screen and let me see how this works. So now share screen. Let me check now. So share screen. So and here. So is this okay?
Yeah, yes.
Okay. Can you see my slide?
Yes, Professor.
Yes. So now
you can just go for full screen.
Yeah. I'll just try. I'm trying to doing it full screen. It's not going full screen. I'm just trying. Let me check. I'm just doing it full screen so that it will be okay to everyone.
Sir, you can just start your slideshow, then it will be fine.
I'll start. Yes, I'm doing it. It's not doing the full. Let me try again now. Just a second. I'll try. Just a second. Just a second. So now, yes. Now this one. Yes. Now, so is this okay now?
Yes.
It's good. So can you all hear me? Fine. Good. So a very good afternoon to everyone. And It's my pleasure to join this online meeting with you. Thank you very much, Professor Helen, for the introduction. And thank you very much for those who have joined this online event. So I'm myself, Ponadurai Ramasamy. I am basically from the University of Mauritius. I'm also a visiting professor with the University of Johannesburg and the University of South Africa. Today, I will be talking about graphite, graphene, silicene, what is next. But then I will give a brief introduction to the whole field of computational chemistry, computational material science, nanotechnology, before getting into the research that I want to share with you. Now, I'm myself from Mauritius, and I always like to give this slide whenever I'm giving a presentation at international level, because Mauritius is always confused with Malaysia or Mauritania. But with participants from India, I don't think that this should be a problem, because Mauritius is well known to Indians. I always also like to give this slide as a comparison, because this slide is very interesting in the sense that it gives a comparison between Mauritius and India. So Mauritius has an area of about 2,000 kilometers square, and you may realize the area comparison in terms of kilometers square for India. The same thing applies for the population of Mauritius, which is about 1.3 million, whereas the population of India is almost 1.35 billion. So ultimately, there is no comparison both for the area and the population. It's good for me also to share some slides about Mauritius. So Mauritius is famous for the sand, right? So if you but now you have the beach, the sea, and the sun, but unfortunately now, due to the travel restrictions, now you have less or almost no tourists coming to Mauritius. And this is Le Monde Mountain. So this is now officially recognized by the UNESCO. Why it's officially recognized is basically like we had slaves who came to Mauritius. They were hiding in the mountain from their masters, but when their masters came, they jumped to death. And this is a volcano, which is supposed to be a dead volcano, but some scientists mentioning that it may be dormant. I hope that it's not dormant. The day that it may erupt, Mauritius will disappear. Now, this is a slide about the University of Mauritius. Allow me to mention that this is one of the first buildings that among the first buildings which was there when the university started some 50 years back. So you may realize that Mauritius was quite an agricultural country. So the university was meant for agricultural science. But then over the years, we have a full-fledged university with almost 10,000 students. And in chemistry, we have about 300 students from the undergraduate to the PhD level. And myself, I lead the computational chemistry group at the University of Mauritius. And I can say that before I joined the university, there was no computational chemistry being offered. But then over the years, if you see this particular slide where I joined in 2000, so over the years things have improved, right? And ultimately in 2020 we are a full-fledged group with 1 postdoctoral fellow, 2 research assistants, 8 MPhil PhD students graduated, 5 currently doing, 3 MSc students, 5 BSc students, with almost 230 publications. So with this overview, now let me come now to the purpose of the talk today. So today I will be giving an idea about computational chemistry, nanoscience and nanotechnology, our research, our future plans, and of course, I will summarize. And if you have any questions, it will be my pleasure to address. So the basic question is chemistry. So remember that chemistry is a science subject. So like one of the previous speakers gave an excellent presentation about the whole idea of chemistry, the teaching of chemistry, and so on. Remember that chemistry is a science subject. So being a science subject, it is an experimental based subject. You have to do experiments for chemistry. You cannot do chemistry without experiments. But then now you have computational chemistry. So this is the equation which really makes students or others afraid, your fundamental Schrödinger equation. Right. Now, if you allow me, I can briefly explain what is computational chemistry. Now, if you go back to your physical chemistry lectures, you'll realize that the Schrödinger equation can be solved exactly only for one electron system. I mean exactly. So as soon as you have two electrons in the system, you cannot solve exactly. You need to go for approximate methods. So this is the whole concept of computational chemistry, to solve the Schrödinger equation numerically to obtain approximate solution. Remember that it is not possible to obtain the exact solution as such. So then computational chemistry, it really makes use of computers to solve chemistry and interdisciplinary problems, basically trying to have the electronic energy from the Schrödinger equations, but then there are many other parameters from which you can calculate, which you can extract. And it satisfies one of the fundamentals of green chemistry, except that, of course, you keep on dumping all these computers around, and you should have means and ways to control. Now, you do have different applications of computational chemistry, ranging from electronic structures of existing and novel molecules, complexes and clusters, thermodynamic, spectroscopic, and kinetic parameters of molecular species, global warming potential, global warming species and their reactions in the atmosphere, reaction mechanisms of cycloaddition and nucleophilic substitution, among others, solar dyes and their efficiencies, drugs and their applications, interdisciplinary fields such as astrochemistry and biochemistry. Of course, I will not go through all these in just one lecture or talk which I am giving. I will be focusing to drive towards the title of the presentation. And you'll realize that the subject, computational chemistry, it has progressed over the years. And recently we had the Nobel Prize in 2013, right, awarded to 3 eminent scientists for their use of computational chemistry to model complex chemical systems. And of course, if we go back, we all know about the Nobel Prize awarded in computational chemistry by Walter Kohn and John Pople. Now, having talked about computational chemistry, let me go down now to nanoscience. Right. So what is nanoscience? So if you split the word nano and science. So nano is a Greek word coming for dwarf, small, the study and manufacture of extremely small particles. But then you see science has to be precise. You cannot just tell me small. So small relative to what? You need to have the number. So here this is a nice slide which really gives you an idea about how to go for an understanding of the size structure. When we are talking about a macro structure, I'm referring to an apple. You go for a microstructure. For example, you refer to the human hair, but you go down to the nanoscale, 10 to the power minus 9. You go to the atomic scale, where now you talk about the nanostructure, nanoscale, which is almost 1/1000th of a meter. Now, these give you an idea about what we are talking, right? Just to have a picture interpretation of the macro, micro, and nanostructures. But then, if we know about the nanostructure, what is nanotechnology? The design, characterization, production, and applications devices of structures, devices, and systems by controlling shape and size at nanometer scale. This is, and you find that the nanotechnology, it is quite interdisciplinary, ranging from chemistry to biology to physics, engineering, even medicine, biotechnology, material science, and information science. You can really see how it englobes a quite large range of subjects that you can interpret. And now, let me come now to something which might appear new. It's new, yes, but the field has really evolved about computational nanotechnology. I think you should not find it difficult to understand what I mean. Having explained what is computational chemistry, having explained what is nanotechnology, no doubt you can interpret that computational nanotechnology, so it's a branch of nanotechnology that has really developed and make use of computational science for understanding, analyzing, and predicting the behavioral properties of system relevant to nanotechnology. And you see, you have several papers, important papers, reviews which have appeared. For example, this one, which talks about sustainable nanotechnology, opportunities and challenges for theoretical and computational studies. Allow me to read it in detail. So, to help better understand sophisticated experimental measurements and ultimately guide the design of new experimental investigations, it is essential to conduct theoretical and computational studies on the nano biosurface. So I just have some papers, slides which are to be shared with you that you can go and check about the whole concept of computational nanotechnology. So these are some papers which appeared in Nature Nanotechnology and Nature Material Science. And you see that in these papers, if you can check, these and other computational techniques aid the interpretation of experimental data and propose new directions for experimental work. But then, this is an interesting one. How can ab initio simulation address the risk in nanotechnology? So you'll realize that there are different potential risks and hazards associated with nanomaterials and nanoparticles, but now you have computational methods that really help the nanoscientists to really make use of computations for the prediction. So this is another one where you have the intelligent computational nanotechnology, the role of computational intelligence in the development of nanoscience and nanotechnology. So you realize that ultimately The whole idea is to have a good understanding of the computational methods for you to be able to apply to those systems that you're currently studying. And ultimately, you'll realize that the experiment and theory, you really have a successful cross-fertilization among the two fields, which can really be explored. Now, what is next? I don't know whether you have really read or thought about. Now we are even going in the picotechnology and picoscience. Remember that I talk about the atomic scale, 10 to the power minus 9. Now we go to 1,000 times lower, 10 to the power minus 12. Now, where you find now, you have the picoscale material engineering coming. And this is another paper from a new approach of science, the picoscience and the picotechnology. So this one is nanotechnology and picotechnology to increase tissue growth, a summary of in vivo studies. So having explained about chemistry, computational chemistry, nanotechnology, picotechnology, computational nanotechnology, ultimately computational nanoscience, I'd like to share with you the research going on, which has been going on in the group, in my group, in the direction of graphite to graphene to silicene, ultimately what is next. So the first one is the functionalization of fullerene and graphene. So we all know about the buckyball structure where this was referred, this has been referred as fullerene. And of course, this is the molecule was the famous molecule discovered by this the Harold Kroto, right, for their work for the discovery of fullerenes. And now, after the fullerenes, we all know about the graphite structures. We keep on using pencils for writing up, and we realize that, for example, graphene will consist of different layers. Graphene will consist different layers, like in your the pages of your book. But then graphite, sorry, what will be graphene? Just one layer atomic scale. So from your graphite, you end up with just one layer atomic scale, which is the graphene. Now, and of course, this was recently the Nobel Prize, well, not recently, some 10 years back, awarded to two scientists. Now, what is our interest in the fullerene and graphene is basically in terms of their hydrogenation and fluorination, because ultimately these compounds have exceptional characteristics, the organic metallic chemistry and inorganic chemistry. So this is the simplest cycloaddition reaction to an alkene. So in this one, we have the Diels-Alder reaction, where you are having a video being displayed. So this video is being displayed not by just manipulating the formation of bonds, but precisely from the calculation, the intrinsic reaction coordinates, which gives you how the reactants are joining to each other. And in this particular one, the ethene and the diene, they are symmetric with each other. So you have simultaneous formation of bonds at the transition state, which is the synchronous way of forming the bond. Otherwise, you can have one bond forming followed by the other, which will be asynchronous. So computational methods can really help you to have a picture at the molecular level how the bonds are forming. So if we have now a 1,3 dipolar cycloaddition where we have a dipolarophile and a 1,3 dipole, we end up in a ring. So this is the cycloaddition reaction. And if you go to the literature, you'll find that there are several papers about 1,3 dipolar cycloaddition reactions, in particular to the graphene or the fullerenes and so on. But then we were interested to see how, for example, you can have the cycloaddition reaction to the fullerenes. And remember that you have the C60, and we've compared it with your classical ethene molecule. We've compared whatever we've obtained for the fullerene with ethene molecule. So and we considered all the different possibilities of adding to the 6,6 double bond, 5,6 double bond, and ultimately the close 6,6 possibility and the 5,6 possibility. And we observed that theoretically, if we have fluorine as a substituent for the RCNO, we have an abnormal low activation energy, and which should really help for the synthesis. But we did not explore too much about the stability, and we look forward that the experimentalists, they really synthesize the fluoroderivative of the fullerene. So this is what I said. It has an abnormally low activation energy and an unexpected fast rate of reaction. So this we published some years back as an invited paper in Heterocycles. So we've extended now the 1,3 dipolar cycloaddition to graphene, right? But then, of course, you can't just take the whole model. So what we are currently doing, we are looking at ethene at 1 ring, 2 rings, have 2 by 2, 3 by 3, 5 by 5, 6 by 6. The idea is to see where you get a convergence in the results for you to be able to use the appropriate number of rings to achieve the results that you would expect from graphene itself. This is currently going on in the lab. And like I said, we are looking at addition at the center, at the corner, and at the edge. So hopefully this project should be completed and we will publish the results. So these are some preliminary results which I'm sharing with you, where you have addition to the graphene layer structure. And of course, again, this is the IRC. Remember that in the case that I shared with you before, you had symmetric structure where you had the synchronous formation of bonds. But here, carbon and oxygen, they will form an asynchronous way. If you see here, the carbon is being formed, carbon-carbon bond form, and then this is followed by carbon-oxygen, asynchronous mechanism. Like I said, we are trying to see the addition at different possibilities, right? And then also trying other possible substituent for the cycloaddition. So this project is also going on. Our next part of the research is the novel 2D material. Like I said, you know very well about the graphene structure, right? Where you have 1 layer carbon structure, but graphene is being used in batteries, composites, high performance sensors, in the medical field, oil fields, paints coating, printing and packaging, sport equipment, supercapacitors and transistors. But then you should not forget that silicon is just below carbon in the periodic table. So what about to have the silicon analog of graphene, right? So you have now the electronic structure of silicon-based nanostructures. So this is the structure predicted by the group in doing the calculation. The only difference I hope you can see is that silicene is not expected to be planar, just like graphene, right? So in fact, this silicene, the calculations were carried out by a group, Professor Locke, who's supposed to be the father of silicene, and he visited the group for almost 3 weeks, and we have a project that we are currently working in this direction. So what are we doing? Like I said, we are moving from carbon to silicon. Remember that the graphene is planar, whereas the silicene is non-planar. But what we are interested, like I said, so this is the rise of the silicene, but we are interested in other aspects. If you go to literature, you will find some papers related to these graphene and the two-dimensional silicon, and so on and so on, right? But what we are interested is to look at other possibilities. For example, we talk about the graphene, silicene. What about going to germanium? What about going to tin? What about going to lead? And what about going to the other direction, borofin, right? So some of these structures I mentioned, they have been studied, but then we have a project based on looking at other possibilities. For example, this one has aluminum, right? But then going even down to indium. But then we are interested in having, for example, the 2D structures involving gallium and even thallium, right? So this is a project that we really started because the boron analog is known, the aluminum analog you have in literature, the indium analog you have, but you don't have much information about the gallium and the thallium analog. So this is the project, and it's almost done, and we will be publishing soon. Now, the projects which I shared with you in the direction graphene to silicene and what is next, they are almost fundamentals. But we also have some parts of our research dedicated towards applications. So one of the application of the nanoparticles is in the treatment of wastewater, right? So you may realize that water is crucial for life. You have lots of water pollution, but then some people are not having safe water for drinking, and therefore there is a need in this world to be able to clean water pollution, wastewater, right? And this is one of the sustainable goal number 6, ensure the availability and sustainable management of water and sanitation for all. Basically, you see that wastewater can be treated by biodegradation, ozonation, electrosorption, and adsorption. But then if you go to the literature, you'll find that nanoparticles, they can play an important role for the extraction of pollutants from water and soil. And so this is one of the papers that we published in collaboration with Indian collaborators, where we've looked at the effective adsorption of pyridine on silica-derived de-oiled mustard cake. This was a combined experimental and theoretical. The experimental study was done in India, and we did the computational studies. So, and the next one, which is also an interesting one, for the removal, where we've used the palladium decorated zinc oxide expanded graphite electrode for the removal of 4-nitrophenol. So the experimental part was done in South Africa, and the student came and spent some time in Mauritius for the computational studies. Ultimately, we could explain how about the removal of the mechanism involved for the 4-nitrophenol. So this is a good complement between the computational and the experimental studies. So I hope in the 40 minutes that I had about the talk, I could explain to you about computational chemistry. I could explain to you what is nanotechnology, what is picotechnology, and what is computational nanotechnology. I've driven the talk from graphite to graphene to silicene, and most probably what is next. Of course, an overview of the research going on in the lab using theoretical methods to study nano compounds. Our future objectives, we are interested to have more collaboration, particularly with experimentalists and the industry, and we are more interested to have more of applied research. Right? You should.
We have to summarize now. We are getting late.
Yes. So the research has to be directed toward the country needs, and of course, communication to the public. You're invited to collaborate with us. You can check our website, and you can check for some of the possibilities to travel to the group, but now this has been suspended due to COVID. And of course, I need to acknowledge all the organizers of this conference, in particular Professor Prem Mishra, who invited me, and Professor Prabhu, who is in constant touch with me, the University of Johannesburg, the University of Mauritius, the Tertiary Education Commission, the Mauritius Research Council, the Grid Camp for Computations, and all members of the Computational Chemistry Group. So thank you. If you have any questions, I'll be pleased to answer. I'm sorry if I've taken some extra minutes to come. Thank you very much.
Thank you so much, sir. Thank you so much, Professor, for your excellent presentation on computational chemistry. For want of time, we are not entertaining any questions here, and I ask the participants, if you have any queries, you can just contact Professor Ponnudhari Ramasamy, sir. He'll be there to help you out, and he's a very nice person, and definitely answer all the queries through your mail. Thank you so much, Professor Ramasamy, sir. Thank you.
Has been my pleasure. Yes.
Yeah, we have a next speaker with us, Dr. Andrew Chandler, a senior lecturer in science education, University of Brinton, England, United Kingdom. I'm very privileged to introduce our speaker today. Andy Chandler was a science teacher in south of England for over a decade before embarking on a doctorate in assessment in science education. Since then, Andy has worked part-time for the University of Sussex, training pre-service science teachers, and moved to the University of Brinton in 2019 to become a senior lecturer in science education. Andy specializes in education consultationally in Canada and China. Andy has published over 50 titles of resource books that support science teachers with classroom assessment since 2013. Andy has been the assessment editor for Oxford University Press, working on best-selling textbooks for secondary school science in England. Recently, he has authored 2 books with Oxford University Press, How to Assess Your Students and How to Teach for Progress. Currently, he is working on a large curriculum project for science with Oxford University Press. Dr. Andy is an active member of the Association for Science Education with roles as Regional Chair and the National Committee for Science Education 11 to 19. Andy also regularly writes for Education and Chemistry, a Royal Society for Chemistry publication on the topics including formative assessment, self-regulation, and teacher well-being. We are very happy and honored to have Dr. Andy with us for this NCCT program. Very happy to welcome you, Dr. Andy, on behalf of the organizers. Now over to Dr. Andy.
Thank you very much. Thank you so much for inviting me. I'm honoured to be here. I'm just going to share my screen so that you can see my presentation. So I will get that and then I can start. There we go. Share screen. Screen share. So now you can see everything, but hopefully we can show you this. Okay, can everybody see? Helena, can you see okay?
Yes, Dr.
Yep,
Andy.
that's good. Thank you very much indeed. Right. So, thank you very much. I'm going to talk to you about assessment literacy, which is something I've got very interested in over the last 5 years or so, partly because I train teachers to teach science in Brighton, and I see how they develop with their teaching and how children learn, but not necessarily how they develop in their assessment. It's always the thing that seems to be the last thing they worry about. And I argue that we should be taking putting much more attention on assessment literacy. So I'll explain what that is and what I do. I've got my email here, which I'll put out as well. If anybody wants this presentation, they're very welcome to it. So my outline is, how can developing science teachers' assessment literacy improve student progress? And this is the thing that I started with, is how can we improve student progress? And I think it's, if teachers have a good sense of assessment literacy, we can do that. So I'm going to look at the strategies for developing that, the frameworks of thought, and the classroom strategies that can be used. I will mainly be dealing with people who are teaching students at what we call Key Stage 3, which are 11 to 14-year-olds. Okay, so we'll be looking at quite the younger end of students. The presentations so far have been for undergraduates and children that are slightly older. So the examples I give here are of teaching younger children. Now, as I said, teaching, learning, and assessment are all three important areas of being a good educator, and having a good understanding how to teach, how children learn, and how to make assessments, how to judge how well that learning's going, are very important and very much intertwined. And so I want to just talk about assessment literacy. There's a lot of discussion about assessment literacy and what it means, but my favorite definition at the moment is the knowledge about how to assess what students know and can do, interpret the results of those assessments, and apply the results to improve learning and program effectiveness. So I am very, very proactive about formative assessment. So the assessment that goes on in the classroom, through the discussions you have with students, through the judgments you make day to day, minute by minute as a teacher. I'm very interested in those parts. In existence at the moment, we talk a lot about pedagogical content knowledge of teachers, PCK, which is where our subject knowledge overlaps with their pedagogical knowledge. And I argue that our pedagogical knowledge should also have a strong emphasis on our knowledge of assessment and our skills in assessment. And at the moment, I feel that that is often the least considered area. So the research base for this, it comes around that in 1991, Stiggins first talked about assessment literacy, and in educational professionals, the idea that we underemphasize the assessment part of our skill set. And he says, what does assessment tell students about the achievement outcomes we value, and what is the likely effect of assessment on students? So those are the things he put forward. But since then, there's been quite a lot of research in these various areas. The assessment literacy of pre-service teachers, so how well pre-service teachers are able to understand assessment. The assessment literacy of teachers generally. And finally, particular focus on the assessment of there's particular emphasis on teaching English as a foreign language. There seems to be a big interest in the assessment literacy of teachers. So these are these teachers. So these are the areas. But recently, 2016, we've had a reconceptualization of teacher assessment literacy, and they put forward 7 areas that should be developed. Now, I work with teachers day to day, training teachers and working with these existing teachers, and always thinking about how I can best support teachers in teaching and learning and assessment. And I've come up with my own, from the research, I've come up with my own areas that I think are the most important to develop. And these are the areas I'm going to discuss. So these are the 6 elements of teacher assessment literacy. I am very interested in how we can develop these, and I'm going to give you just one example of each area as an introduction today. So I've called these the 6 elements because we're in chemistry. I thought elements of science teacher assessment would be helpful. So we're looking at assessment skills. We're looking at the knowledge of mistakes, errors, and misconceptions. We are looking at interpretation and intervention, those skills that we have as teachers, our policy knowledge, our understanding of exam technique, and our critical engagement with assessment. So element 1, assessment skills. The assessment for learning cycle, right back from Black and Williams' original work, and more recently a summary of how that's all moved forward from Harrison and Heritage, we have the assessment for learning cycle, which is where students ask, where am I now, where am I going, and how do I get there? And if we use this as our main way of planning when we're a teacher, and we're thinking about what we're teaching, we think about where are the students now, where do we want to get them to, and how am I going to get them there? And if we are if we start to expand that through all the different areas of the content of which we're teaching, we start to have a mental map of chemistry teachers. And I've got very interested in the mental map of science teachers in general, of what is the area that they have planned out. How do they know that if a child is on the right path to get to where we want to get them to, or if they're deviating from that path, how do we get them back onto that path? So all those ideas are in our head. So when you're a skilled science teacher, a skilled chemistry teacher, when you're talking to a student or you look at a piece of their work, you can see whether your map matches their map, and then you might start to make some decisions about how to get them to understand the map that you've got as a chemistry teacher. Very interestingly, the session before last was sort of talking about some of those things. You know, and one of the big questions is the chemistry teacher's mental map the right map right now? But we won't go into that just yet, but that will be part of the critical part of that. So how do we reveal a chemistry teacher's mental map? What I've been doing when I go out and do some training with schools is I give them this this classic experiment that we do with 11 to 14-year-olds. We show a displacement reaction. This is an experiment where you can just show it. But what I ask the chemistry teachers to do is, what is the prior knowledge required before you can even show this experiment? What is the new knowledge required that you're trying to teach? And then what would that understanding lead to? So it is, where am I now? What do I know already? What do I want to understand? And how am I going to get there? And so an example of the types of things people will write is new knowledge. We're looking at displacement reactions, a specific example of copper sulfate and magnesium reacting, and the specific changes in chemical reactions. So this is a specific example of a chemical reaction. But before then, our students need to know about metals and non-metals, atoms, elements and compounds, and chemical reactions, the types and features of chemical reactions. And this, at this stage, will lead us on to later knowledge. So symbol equations, reactivity series, various other parts of chemical science as well. But it's a particular moment where students are aware of displacement reactions, and this is often the experiment that we teach. So this is building our terrain, understanding what is in our mind, what the pathway is, if you like. So this leads us to element 2, and this is knowledge of mistakes, errors, and misconceptions. Research base for this, I've learned a lot from Keith Tabor, who's at Cambridge University, and he identifies common reasons for mistakes for learning, which I'm going to go into more detail in a moment, because I found that one of the most helpful ways of doing this. But there's also a lot of research in the assessment mistakes and learning deficits, and how it can be used to enhance learning if teachers have a good understanding of how children make mistakes and their motivation. Driver et al. Did lots of work in identifying misconceptions, and there's something that is an amazing piece of work at the moment that is based at the University of York, are called the best evidence science teaching, which has a lot of basically they produced progression maps with all the possible misconceptions and so on. So they're actually taking this very far, and it's a very useful resource for teachers. Now, the types of mistake that Tabor I was talking about talks about is when a child makes a mistake. There are 4 possible reasons. There is a lack of knowledge, a missing connection, a misconception, or a misunderstanding. And depending on what type of reason there is for that mistake, the intervention, there's a different type of intervention. So if there's a lack of knowledge, we do a making good activity, which I'll show you some examples shortly. So basically we're filling in the gaps they're missing. If there's a missing connection, we can show them how give them a connecting activity to make a connection. And if there's a misconception, we can do a dissociation activity. And those are the ones that are the most difficult, because misconceptions are very strongly held, and it takes quite a while if you understand about misconceptions to actually change a child's mind about something that they've thought about previously. Also, there's some argument which I go with as well, that misconceptions, we don't actually ever get rid of misconceptions, we just know there's an alternate way of thinking, so we keep that schema of our misconception, but we know that there's a scientific way of understanding the world, and we have an alternative schema that goes alongside that. And then finally, misunderstandings can be challenged through a correcting activity. Now, the modes I've got here, pupil-led or teacher-led, I think I've made tasks before where we look at lack of knowledge or missing connections, and you can actually just give activities to students to work their way through, to fill in the gaps, or to make the right connections. Often teacher-led interventions need to be for the misconceptions, misunderstandings. They're much harder to understand. So moving on from this then, what are the common errors and misconceptions of this particular example, which is my running example? And when I use this with teachers, they come up with, sometimes because of the change in color, students think that the magnesium is rusting, which it isn't, but that is a perception. We have the idea of language, where we say a colorless solution is described as clear or white, and there's word equation errors and symbol equation errors, and probably a whole heap of other things as well. But when we are thinking about a teacher's terrain, their map, we can add these things in, and we often talk about these as either potholes where people can fall down a hole, and or it's much more difficult to understand, so it's like a steeper terrain. We're moving up a steeper terrain, so the more possibility there is of misconceptions, misunderstandings, the harder the terrain is. So teachers need on their map to know what these are, so that they are really ready to challenge them.
I'm going with it.
So element 3, once we've identified these issues and realize that children aren't following the map we hope, we are ready to interpret and intervene. And one of the biggest things in science teachers' skill set is noticing these gaps. And there's been a lot of research by Bell and Cowie, particularly, on this idea of noticing where a child is and where they're going. How do we notice these gaps, these discrepancies, these mistakes, errors, and misconceptions as teachers? How do we move children forward? How do we get them back on the pathway that we think they should be taking? So this idea of where am I now, getting an idea of where a child is right now and how we're going to move them on is a really important skill of a teacher, and it does need to be encouraged to be developed. Okay, so this skill of noticing in the classroom is very, very important. So when I see a child do this, do I have something I can do to get them back on the path that I need them to be on, the understanding that I need them to be on? So as I talked about with the interventions based on Tabor, well, how do I get back on the path where I need to be? So making good activities are often focused on missing knowledge. So for example, keywords and meanings. So making sure that they've got those clear links, giving them comprehension questions, revisiting specific knowledge or content, so just going over it again or going over it in a different way, or identification of key processes, so that the idea that they understand, in this case, what displacement is, what it means, and that this is an example of it. Connecting activities for missing connections often involve them comparing contrasting ideas. So you could compare displacement with rusting, so oxidation with displacement, building a concept map so they get an idea of the terrain themselves, and often there's lots of overlap between this idea of a mental model and a concept map, and also sequencing events so they can actually see how these events fit in. In terms of a chemical reaction, what's happening before, what's happening during, and what you left with. And then finally, correcting and dissociating activities for misunderstandings and misconceptions. I think often it works much better with a demonstration live with questioning, so that you can actually talk it through, pick up where children misunderstand, pick up where their knowledge is lacking, pick up what their real misunderstanding is. And the same questions, we can put the same questions asked differently, and we can have spoken and written explanations as well, so that we are working through those. And these are all good interventions to when students are missing knowledge. And this can be applied at all levels. It's not just this low level, it's just to try and this high school level. This is just a set of examples. So the interventions here, being clear about the key words, being clear about what prior knowledge is. It is always worth going back. So when we are making assessments, when we're assessing where someone is, making that judgment, we need to check that that prior knowledge is there before we can move on. So the idea of elements and compounds, the fact that there's chemical reactions and word equations, and then making connections. You know, a color change isn't just rust. There's other alternatives as well. There's different types of chemical reaction. So this is our approach to interventions. But then we've got, as a teacher, you need to have a good idea of policy. You need to know what is required of the students at particular stages of their learning. So if there's statutory assessments, what are those statutory assessments? What's their structure? How can that data be used? Can we look at previous data from statutory assessments to understand what we need to teach our students, and what the limitations of the statutory assessment? So what are the problems associated with them as well? And one of the big areas is the washback effect. And teachers need to have a good understanding of the washback effect so that they can know the positive effects and the negative effects. So for example, well, the washback effect is any change that we make as a teacher or a learner based on the needs of assessment. Okay, so if an assessment, so this is like a test, if the assessment is Sorry, I'm just seeing things flash. I'm going to put that there because otherwise you can see it. If there's any changes that you make as a teacher, is that for the benefit of the child's learning, or is it for the benefit of the test? And we have to make those things clear. So positive effects is that we have positive preparation for tests, but it becomes a negative problem, a negative effect, when teachers are teaching to the test, or we only teach what the test covers. So this is the big issue. If we are asking, if we just say, right, as a teacher, we're just going to only focus on the test and not chemistry as a whole, then there's an issue because we're missing out a lot of chemistry. We're only preparing students for a particular test. However, there are times where we do need to prepare students for a particular test at a particular time, and that is our element 5. So if we are taking a particular test, do we know all the areas? So these are the questions I ask teachers, whether they know about a test and the examination technique you can use. So do you know the types of questions that are asked in this particular exam? Do you know the type of responses that are required by the examiner? Do you know the common mistakes that are made in these exams, and can we make sure that students miss them? Don't do them, or at least challenge them, let them be aware of the common mistakes that are made. Do you know how students can best gain credit for their marks? And are you giving students opportunity that they can learn? Sorry, I don't know whether somebody's asking a question or whether they've just got their microphone on. Can you check your microphones are off? Because I can hear various voices and I'm not sure if you're asking questions. Anyway, I'm going to try and continue. There we go. I have, so the final one is we need to make sure students know how to answer the types of questions, the style of questions there are. So another element of being assessment literate is having this awareness. And then finally, I've got critical engagement with assessment. So teachers need to understand what assessments are and what they're using. Now, the approaches to assessment, I'm very keen on classroom assessment, formative assessment, that day-to-day assessment that we do. We have lots of issues with people using assessments inappropriately. So have we got the right test for the right purpose? Are we just giving students lots of tests for the sake of it? What is the purpose of that assessment that we're giving? Are we using multiple choice questions? Are we getting them to write essays? What are the advantages and disadvantages of those? And also, what is the reliability of the assessment you're giving, and the validity of the inferences you're making from that assessment? So is that so are you making a judgment that is appropriate to the type of test that you have made? So just because they can answer an assessment that asks a question about displacement reactions doesn't mean to say that they know about all types of chemical reactions. So how do we make judgments about how the types of the types of chemical reactions that students know about? So we can we can ask those questions. And then designing and critiquing assessment, we are looking at when you're a teacher, can you look at a test and say to yourself, I know what this is about, I know what we're actually going to assess, and I know how we're going to use it, and the information will be useful to the student and to me as a teacher so that I can improve my teaching and learning. So that is the way we can talk about criticality, but there is a whole range here of criticality, and the criticality is a really important part of being a teacher, so you know what assessments you're using and why you're using them. So how can we support chemistry teachers to develop assessment literacy? Well, I've taken this as 3 stages: the knowledge, the application, and the critical understanding. We need knowledge of specification, assessment criteria, and qualification structure, but we need application and this bit is the most important bit to me, is the teaching effectively, assessing effectively in the classroom, and intervening effectively, because students make the best progress when we're able to do those things. And then finally, we need a critical understanding of assessment approaches, of qualification structures. We need to know the advantages and disadvantages and the limitations of what we're using. So the assessment of the journey of assessment literacy is ongoing. It's something that's an important part of being a teacher, and there are 6 main areas. And I would get you to reflect on, you know, what has, if you're a teacher, what influenced your assessment learning? I'll say that again. What has influenced your understanding of assessment? What would be your next steps for improving it? Is there a particular area of these 6 that you'd like to improve? And if you are a leader in teaching, if you're a head of department and you lead other teachers, or you're involved in teacher training, how might you support other teachers developing their assessment literacy? Now, I've talked about these areas, and there's the bibliography for you. So if you want to follow anything up, it's there. I talk about this much more in my assessment book. And if you want to use this process with your science teachers, I've got a couple of slides here to help that. I have got, these are the questions I ask. This is a slide I use, and for a particular teaching activity, teaching area. So sometimes I just say, okay, then if we are teaching about synthetic chemistry, what are the areas? What are the processes? What are the key knowledge and understanding? How are these areas connected? Is there a hierarchy? What needs to come first? What comes later? What are the common misconceptions, mistakes? And is there a good pathway that we can help develop our students to go on? And then finally, you can discuss the activity. Often teachers will compare their maps with one another and move on with their understanding. So for example, a skilled teacher who's got lots of experience compared with a novice teacher will have a very different terrain, a very different mental map, but they can compare and they can learn from each other. They can learn where there are limitations in one earlier, and where there is in the naive one, in the person who is novice, and the novice can learn from the expert. So working together in groups really helps as well. I hope that's been relatively short, but I hope it's been of use. I was given 45 minutes. I think I'm just about just under that. So I don't think you're taking questions, but I'm very happy to have people send me questions, or if you'd like the PowerPoint, I'm very happy for that as well. Thank you very much for inviting me. Okay.
Dr. Hendan Kavita, Professor Prem Mohan Mishra.
Yes, sir. Hello.
Hello.
Yeah.
Sir, you're audible. You're audible. Mishra, sir, you're audible.
Yeah. What problem, Roj?
Helen, madam.
Dr. Andy has finished his presentation.
Yeah.
Helen, madam.
Thank you.
Thank you, sir. Thank you, sir, for your wonderful presentation. We have learned many things from you. Thank you, sir. May I now request Professor Sudha Jain, madam, from University of Lucknow and ex-president of ACT, to chair the valedictory session. Over to you, ma'am.
Professor Nageshwar has joined. Saniji, please. But we are given time at 4 p.m. Sorry, Amritji.
Okay.
Amritji.
Okay, sir.
You are getting me?
Yes, sir.
We have given time to Nageshwar Rao at 4 p.m.
Yes,
In
sir.
the late sessions, we have changed the schedule slightly.
Okay, sir.
We have to wait for 20 minutes.
Are we on?
Okay.
Have I finished too early?
No, no.
No, that's right. I thought we were running late.
But we are late sometimes. So.
And sometimes we're early. That's absolutely fine.
Well,
I'm happy to answer any questions if anybody has any questions.
Yeah.
You may have some.
We may have question answer session. If any participant have any question, you can ask. And the lecture session will start at 4 p.m.
I can see a question from someone about doing this through the online mode. We obviously in the UK at the moment we've got our COVID restrictions as well. So there's not been as many practicals as you normally have in school. I am very pro if you've got the chance to do face-to-face using equipment, that is the best way because children can see things happening live. But there are online opportunities, and many teachers here are recording their practical work, and they're putting videos online, or they're doing it live, and they use things called visualizers where you can do good close-up chemistry. There's something people are doing called microscale chemistry, which is very good because you use small amounts of chemicals, and it shows students what's happening, and you can interact with them live. But the big issue is in assessment. I mean, for me, assessment is listening to students, seeing what they're saying, what they're doing, and understanding where they're at and how do we move them on. So you can do assessment online, but and there are lots of ways and there's lots of structures. It becomes a bit more formal. So for that Tabor, Keith Tabor's when a child makes a mistake, you can often use that as a structure on which to understand what mistake a child has made. And when it's online, you can have a number of activities depending on what activity there is. I hope that sort of answers. If you don't know about microscale chemistry, I'll be able to send you a link to microscale chemistry. Any method for slow learners? Well, I think the big thing about teaching, being a teacher live in the classroom, you can accommodate slower learners by often it's the first problem, their lack of knowledge, and you have to go back on it. So that Tabor's mistake is usually lack of knowledge because they haven't grasped that first bit. So it's always worth going back, and the intervention is to go over either their missing gaps, what they're missing in knowledge, or what their misunderstandings are before moving them on. And sometimes it's just doing another work. There's been microscale, somebody says there's microscale sessions by the RSC. Yep, that's right. So I don't know whether you've had any of those sessions here, but I can send you a link from the RSC to those if that's helpful. Some of you are sending me your email. If you just send me an email, I'll reply with my PowerPoint for you. I think that'd be helpful. I don't think I'll be able to take all of these emails from the online chat very easily. Is there any other questions?
Are there any questions? If there are no questions, thank you very much, Dr. Andrew, for your.
Thank you, Helen. And thank you, everyone.
I think there is one more question. Like, our books are available for this one. There's a question like.
Yep, the books there are available on the Amazon Indian Amazon. I've checked, so they're there. You can just type them into Amazon, and they will link you to them. So the assessment one and the progress one is there, from what I understand.
Okay.
Thank you.
Okay, thank you, Dr. Andrew.
Thank you, everybody.
Thank you.
Have a lovely rest of your day.
Yeah, thank you so much. I thank all the speakers who are in this technical session, who has given an excellent presentation. Now I thank Professor Mishra sir, Professor Prabhu sir, and Dr. Brajesh sir for giving me an opportunity to chair this technical session. Over to Professor Mishra sir. Dr. Amrit.
Yes, ma'am.
Uh,
Thank you, madam, for chairing this particular session. May I now request Mr. sir. Mr. sir, are you there?
Yeah, I'm getting you. Please, Amritji.
Okay, sir. So should we take a break for 10 minutes?
Yeah. At 3:55, Professor Nageshwar Rao will join.
Okay, sir. Okay, sir.
फोन कर देगा 3:55 शुरू हो जाएगी स्टाफ चाहिए
எனக்கு யாராவது கொஞ்சம் டீ கொடுக்க சொல்லுங்க இந்த பிள்ளைங்கள எத்தனை செஷன் போயிட்டு இருக்கு நாளைக்கு வருமா சரி டைட் செலக்ஷன் நாளைக்கா
I was in California and all the rice there is from Thailand. I asked, why do you not
हाँ 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 सुधा जैन हेलो चल रहा है Hello, Amrit ji. Are you getting me?
Yes, sir.
Yeah, please start.
Okay, sir.
You got the program on your mail?
Yes, sir.
Likewise, change the time.
Just a minute, sir. Yes, sir.
Yeah.
Let us start, sir.
Yeah. Sunny ji, please unmute Sudha ma'am. Sunny ji, are you getting my sound? Hello, Sunny ji. Sunny not present?
Yes, sir, I am here. I have provided course rights to Sudha ma'am.
Sudha ma'am. Professor Dolly Sinha.
I'm here.
Yeah. And Professor Nageshwar Rao. Professor Hemant Khanolikar. And Professor D.V. Prabhu. Hemant ji is there? Hello, Hemant ji.
Sir, wait for a while. मैं सबको का mute हटा रहा हूँ तो people now can unmute themselves.
Okay, okay.
Sir, now everyone can unmute himself or herself.
जी बताएं
हेमंत जी
नागेश्वर राव पीसी इग्नू
या सर नमस्कार
नमस्कार नमस्कार जी
थैंक यू सर सॉरी फॉर लेट
नहीं कोई बात नहीं
because we have many speakers so okay Amrit ji please start.
Thank you, sir. May I now request Professor Sudha Jain, Madam, from University of Lucknow. She was the ex-president of ACT, to chair the valedictory session. Over to you, Madam.
Thank you, Dr. Amrit. First of all, I would like to extend my heartfelt thanks to Professor Prem Mohan Mishra for giving me this opportunity to chair the session. I welcome Professor Nageshwar Rao, Vice Chancellor, IGNOU, New Delhi. And also I would like to welcome Professor Dolly Sinha, Vice Chancellor, Lalit Narayan Mithila University, Darbhanga, to this valedictory session. All the participants, they are also welcomed for this valedictory session. As you know, today is the last day of NCCT 2020 and the International WebCon on recent advances in chemistry education and chemical research. I congratulate Professor Prem Mohan Mishra and his entire team for this successful event. During these 3 days, they have left no stone unturned to make this event a great successful event. Congratulations, sir. All the speakers,
Thank you.
all the deliberations, all the speakers. I would like to mention that I have been associated with this NCCT and this ACT from its inception. And this is for the first time we had so much abroad contribution here. We had so many delegates from outside India, all the main bodies of chemistry, whether it is IUPAC, Royal Society of Chemistry, American Chemical Society, all have contributed, all have given their deliberations, very excellent deliberations and very thought-provoking. We had all the 3 days, the lectures were very thought-provoking. And all the lectures have covered mostly each and every aspects that is required to make the chemistry education more useful and attractive. I am sure by adopting these tools, the students will be interested to opt for chemistry from the beginning. As yesterday we have heard, from class 6 to 10, 6 to 12, we had to change the curriculum and we have to change the mode of teaching. So that will attract the students to opt chemistry, and further also the students will be motivated to apply this chemistry knowledge to their daily life. Once again, I congratulate Dr. Mishra and I welcome all the guests over here for this valedictory session. Thank you very much. Hello.
Yeah. I can see Brajesh Pare has joined.
Oh. Dr. Pare?
Pare is there. Brajesh Pare, sir, who have joined.
I have seen his name.
Yeah, I have also seen. No problem. Hemant, you're not there? Hemant, you go ahead.
Okay. Hello. May I now?
Prabhu.
Hemant Khanolkar,
Yeah,
Treasurer
he
of.
is here.
Yeah. Hello.
Yeah.
Hello.
Yeah.
Can you hear me, sir?
Yeah.
Yes.
We're getting
Yeah.
your-
Okay.
Go ahead.
Yes. Good evening, one and all. So I, Dr. Hemant Khanolkar, extend you a warm welcome to valedictory function of 3-day national conference for chemistry teachers NCCT 2020 and international webcon on recent advances in chemistry education and chemical research spanned over these 3 days. The talks by the eminent people provided us opportunity to understand the ongoing trends, opportunities and challenges in chemistry education as well as chemistry research. And I welcome our chief guest for today, Professor Nageshwar Rao, Vice Chancellor, Indira Gandhi National Open University, and guest of honor, Professor Dolly Sinha, Pro Vice Chancellor, LNMU University, Darbhanga. Without much ado, now I invite Professor D.V. Prabhu, General Secretary, ACT, to give his address.
Thank you, Hemantji.
Thank you, Hemant. Good afternoon, dear friends. A special welcome to Professor Nageshwar Rao, the Honorable Vice Chancellor, IGNOU, New Delhi, and Professor Dolly Sinha, Pro Vice Chancellor, LNMU, Darbhanga. I would like to also welcome very specially Shailendra Jain, our former EC member. Welcome, sir. We are almost at the end of 2020, and all of us have gained a good exposure to the new development in chemistry and chemistry education. And through the various speakers, we have come to know what is happening at the frontier areas of chemistry. Now it is a time to pause and reflect on the path to be taken by ACT and to prepare a roadmap for the future. ACT was started way back in 2000 to promote excellence in chemistry education. And during the last 20 years, the organization has achieved significant progress in reaching out to chemistry teachers across the country, and organizing a large number of activities for teachers, researchers, students, and industry which includes national and international conferences and workshops. When it started in 2000, the mandate given to ACT was 1. To advance chemistry education in the country by means of curriculum development and innovation in teaching methods. 2. To forge a vibrant synergistic relationship between academia, industry, and research for mutual benefit. 3. To explore and nurture talent in chemistry with reference to the Indian National and International Chemistry Olympiad programs. And 4. To collaborate with international science teacher organizations for organizing joint programs and exchange of ideas. Looking back on the past 20 years, we can say that the Association of Chemistry Teachers has been able to fulfill many of these objectives. This has been done due to the tremendous help and support received from our chemistry colleagues from Homi Bhabha Center for Science Education and the guidance given by the successive directors, starting from Professor Arvind Kumar right up to Professor K. Subramanian, and the help and support received from the chemistry cell of HPSC, especially Professor Savita Ladge, Mrs. Swapna Narvekar, Dr. Indrani Das Sen, and Dr. Ankush Gupta. But a lot needs to be done, you will agree with me, because continuous evolution is the hallmark of a growing organization. So we cannot afford to be stagnant and be blind to new developments. Hence, we have to think ahead and plan accordingly. Fortunately, ACT is having a large cadre of active members across the country, so we can dream big and think of big activities. The recently announced National Education Policy 2020 focuses on, among many other things, an interdisciplinary approach to education, increasing use of technology in education, and enhancing the quality of research. ACT will have to play an important role in all these areas. For us, the roadmap ahead is very clear. In addition to the usual activities, we have to now think of extending the reach of ACT to all parts of our country, especially the smaller cities and towns, and involve those teachers in our ACT work. I'm especially referring to the smaller states like the northeastern states where we have to make an impact. We should make special efforts to organize workshops in experimentation with help from research institutions and industry. This was also stressed by Professor Shivra when he gave his talk this morning. Collaborating with the leading scientific institutions of the country and organizations like American Chemical Society, Royal Society of Chemistry UK, IUPAC, and the Indian Chemical Society to organize joint programs. We have been doing a few of these things, which have to be multiplied. Making the ACT newsletter a powerful vehicle for dissemination of chemistry knowledge, publication of exploring opportunities for training our students in research lab and industry, and also give our teachers an exposure to industrial practices. Many of these things we were discussing in our executive council meeting, and it was resolved that we should try to do some of these things in the coming year. It is our hope that in the coming years, ACT will emerge as a powerful voice of the chemistry educators of our country and will contribute substantially to the development of chemistry education by developing modules for training like monographs, new experiments, textbooks on experiments, so on and so forth. It is with this hope and prayer that all of us in ACT rededicate ourselves to the service of chemistry and chemistry educators of India. Thank you.
Thank you, Professor Prabhu.
Yeah.
And now I invite Professor Nageshwar Rao. I'll give a brief introduction of Professor Nageshwar Rao, and then I request him to speak a few words on this occasion. Professor Nageshwar Rao joined as the Vice Chancellor of Indira Gandhi Open University, IGNOU, which is one of the largest university of the world, and is also Vice Chancellor of Uttarakhand Open University. Professor Rao received DPhil from University of Allahabad and is ICWA from Institute of Cost and Works Accounts, Kolkata. He has written 8 books and has been a VC of Kumaon University, Nainital, and UPRTOU, Allahabad. From 1990, he is a university professor in Pandit Jawaharlal Nehru Institute of Management and also at Vikram University, Ujjain, where he was a director for 13 years and has been the faculty dean of management study at Vikram University. Now I request Professor Nageshwar Rao to give his address.
Thank you very much for giving me an opportunity to be with you this evening. Distinguished guest, Professor Dolly Sinha, Pro Vice Chancellor, LNMU Darbhanga, Professor Sudha Jain, President of this association, Brijesh Pare, President ACT, DV Prabhu, General Secretary, and Professor PM Mishra, convener of the program. I must compliment the association, which has taken up a relevant topic, quite relevant to all of us, that is recent advances in chemistry education and chemical research. 3-day virtual deliberations, they have brought useful inferences in the end. And when Professor D.V. Prabhu is narrating the significance and also the outcomes, they really they are very useful to all of us. Chemistry is a discipline which blends and which links other disciplines also. Because chemistry, whenever we look at the science discipline, we find 2 streams emanating from the chemistry. Chemistry, physics, math, and chemistry, then biology and the botany. So life sciences as well as this physical sciences, both are linked to that. Now, when we look at this National Education Policy 2020, it also talks about the multidisciplinary focus. How that chemistry element, it can be expanded to other disciplines also. How the science education can be linked to the humanities. How the science education can be linked to the management. How the science education can be linked to the technology. The time has come when this multidisciplinary focus, it has to be promoted. And in that area, in that arena, this particular association can play a greater role. People are just thinking that how the discipline of science, it can be made much more useful by adding the components of humanities, adding the components of social sciences, adding the components of management. So once we see that multidisciplinary focus will be there, then we can see that how the innovation capabilities of the teachers that can also be strengthened. So the time has come that this blending characteristic of this chemistry, it can be expanded to other areas also. And that is the need which our national education policy has talked about it. And the government of India is moving ahead in this area in a faster way. We know that we are having the SWAYAM platform, which is the biggest platform having 3,000 courses available for almost in all disciplines. Around 1,000 courses they are in the technology and the management, then engineering, and around 1,000 courses they are in the sciences, social sciences and humanities, and around 1,000 courses in the teacher education and other things. And they all are available freely. It is existing since 2016. And around 2 crore people, they have registered on these courses. Free registration is there. When you want a particular certification, then in that case you have to pay. The examination has been conducted by the NTA, National Testing Agency, under MHRD. Credit transfer from this is possible. So a chemistry student can have the study of these humanities by having this SWAYAM platform. Because we know that during this COVID-19, the edX and Coursera, it has come up in a big way in our country. Expanding the base, saying that the course-based learning is more important than the program-based learning. Now, what we are doing is the program-based learning and the course-based learning, they can be integrated further by using this SWAYAM platform. A lot of money has been spent by the government of India. We are having 33 SWAYAM Prabha channels also. They are being used for the delivery mode. They have already got they have already got the science courses in that. They have got the humanities courses. So we all have to think. And since the discipline is very, very specific, blending, it talks about how to mix up those things, how to have a multidisciplinary focus on that. Then in that area, we all can come forward and contribute significantly to the cause of this higher education. I sincerely convey my sincere best wishes on this occasion to all the teachers of the Chemistry Association. Wishing you all the best. Thank you very much.
Thank you, sir.
Thank you, sir. Thank you for your kind words. We have today chancellor, and we now request Professor T.M. Mishra, sir, to introduce Madam to the audience.
Thank you, sir.
Thank you, everyone. It's my pleasure to introduce our Pro Vice Chancellor, Dr. Dolly Sinha, ma'am. She is presently the Pro Vice Chancellor of Lalit Narayan Mithila University, Darbhanga. Prior to the present assignment, she held the post of Pro Vice Chancellor, Patna University, Patna. She has also headed Department of Physics, served as the Dean of Students Welfare, Patna University, and Principal of Magadh Mahila College. She is an enthusiastic, result-oriented teacher, committed researcher, and an institute administrator. She has been involved in education service with experience of more than 39 years. A PhD in physics from IIT Delhi, India. She has published a number of papers in scholarly journals of physics and material science, including the Journal of Applied Physics, USA. Her present area of research is nanocrystalline ferrites and ferroelectrics. She has been awarded many scholarships and fellowships, including the prestigious Teacher Fellow of the Indian Academy of Science, Bangalore, India, and a UGC Visiting Fellow at IIT Delhi. She has presented a number of research papers, chaired a number of sessions, and delivered invited talks, keynote addresses at various conferences, symposium, and seminars, including the 100th Indian Science Congress. Also conducted a large number of national level conferences in basic sciences, social sciences, computers, and ICT and performing arts. She is involved in popularization of science and creating scientific temperament among young people. She has contributed largely in empowering women through education and established the Computer Applications Department in Magadh Mahila College, Patna, and initiated computer education for girl students in the state of Bihar. As an administrator, she has proved herself to be an institution builder. During her tenure as the principal of College, college has scripted many distinctions, including achieving the CPE status by the UGC and re-accredited by the UGC NAAC with A grade. The state government was prompt in recognizing the achievement, and she received the Best College Award from the Honorable Chief Minister of Bihar, Shri Nitish Kumar Ji, on the Shikshak Divas 2013. She has been a member of Board of Studies, Research Council, Senate and Syndicate of Patna University for many years, and also a member of Executive Council of Universities and organizations outside the state. She has been associated with NAC as an assessor for a long. I invite ma'am to bless the question. Dolly ma'am, you are connected.
Am I audible?
Yeah, you are audible.
Hello?
Yeah, you are audible.
Hello? Am I audible?
Yeah, you are audible.
Oh, thank you. Okay. Namaskar and very good afternoon to all. We have amongst us distinguished chief guest of today's event, Professor Nageshwar Rao, Vice Chancellor, IGNOU, Professor Brijesh Pare, President ACT, Professor D.V. Prabhu, GS, ACT, Professor Hemant Khanolkar, Treasurer, ACT, Professor Prem Mohan Mishra, Convener, NCCT, Professor Sudha Jain Ma'am, Dr. Amrit K. Mitra, Professor Sailendra Jain, and many other distinguished academicians and personalities in the audience. Ladies and gentlemen, a very warm welcome from my side to all of you and my dear students. It is a matter of great happiness that on the occasion of 20th year of Association of Chemistry Teachers, an international conference on WAVE has been organized. The 3-day conference is of very high level. The credit of organizing the conference of this level very successfully goes to the office bearers of ACT, and I appreciate their effort wholeheartedly. I am very sure that a large number of teachers and students all over the world have been benefited by the lectures and deliberations during this 3-day conference. Distinguished professors and researchers from various parts of the world, including USA, UK, Canada, Mauritius, India, and many other nations, joined these deliberations. I congratulate the team of Professor Prem Mohan Mishra for successfully conducting this event. This gives me double happiness that the celebration was hosted by one of the colleges of Ellen Mithila University, where I am right now. I congratulate Professor Mishra and his entire team. We are greatly indebted to all the delegates for their active and scholarly contribution. Chemistry, as we all accept, is one of the most important subjects of science. Without chemistry, neither biological science nor the physical science can develop. It is also basic for all kind of allied, subjective, collaborative work among various leading branches of science. And I must mention that not only science, it is equally important for arts and apparels too. All paints involve chemistry, and without it, the canvases of artists and printers will be colorless, and so our clothes. From the toothpaste in the morning to foods and medicines to mouthwash in the night, we are heavily dependent on chemistry. My previous speakers have rightly thrown light on this multidisciplinary approach of chemistry as a subject. A good understanding of chemistry is therefore very important. There is wide scope of employment for students of chemistry. In this context, the topic of the conference, recent advances in chemistry education and research, is very relevant. With the development of technology, the way chemistry has been taught earlier needs to be revisited, particularly in this part of the world. COVID-19 pandemic has also given a great challenge for teaching and research in chemistry. At the same time, we can look at it as an opening up of opportunity to modernize the way chemistry is to be taught in our schools, colleges, and universities. Modern sophisticated instrumentation techniques play a vital and reliable role for the characterization, structure determination, and identification of new molecules. On the basis of these inventions, researchers can modify his or her work according to the need of the industry and serve for the betterment of the society. New advances in science and technology have provided a framework for re-examination of instructional paradigms in teaching, learning, and research in not only chemistry, but all branches of science. We are now in a position to design and implement new learning systems, taking advantage of advances in learning science using technology and reform the chemistry education vastly. Here, I would like to quote unquote Professor Devi, who long ago in the year 1938 stated, "If we teach today's students as we taught yesterday's, we rob our children of tomorrow." His statement, even after so many years, is so relevant. We must integrate the ongoing research activities with our curriculum for teaching chemistry in our schools, colleges, and university. This will enable our students to know what is going on actually in the laboratories and will give them a feel of research that is connected in research labs nowadays, an opportunity to know who are currently the leading scientists and how do they work, the purpose of contemporary science research. What is the purpose of contemporary science research? Simulation is another area which needs to be adopted, as we all know that chemistry is a very experiment-oriented subject and also a source of contamination to our earth. Strategy for capacity building of teachers and laboratory staff is a very important issue in this context. And it is expected that the persons, academicians having expertise in these areas will volunteer to guide and skill other teachers and support staff. The Association of Chemistry Teachers, you have shown that how you can involve the leading chemistry teachers and researchers to in such a way that they can help the next generation of teachers and support staffs to build up a strong human resource who can take chemistry one step forward. Thank you very much.
Thank you, ma'am. The Association of Chemistry Teachers has completed 20 years. The concept of this association was conceived by Professor Devi Prabhu. He is the writer, director, and producer of this association, and he is running it since inception and making it in the shape. So he deserves some appreciation from ACT members. I would like to invite Professor Sudha Jain ma'am to read out the certificate of appreciation to be presented by Professor Dolly Sinha to Dr. Devi Prabhu sir. Sudha ma'am, please. Sudha ma'am, you are getting me? Sudha ma'am, you are getting me?
It's okay?
Yeah.
Am I audible?
Yes, yes. You are audible. Good.
Okay. So thank you, Professor Prem Mohan Mishra, for giving me this opportunity to present this appreciation certificate. It is simply a certificate, not certificate, but our emotions towards Professor D.V. Prabhu, what he has done for making this ACT and for giving this height. So I read out what is written there. Association of Chemistry Teachers, ACT, care of HBCSC TIFR, Mumbai, feels proud to felicitate Professor D.V. Prabhu, ACT General Secretary, in appreciation of his exemplary services to ACT over the last 20 years, since the inception of ACT. Dr. Prabhu is a former head and adjunct professor of chemistry at Wilson College, Mumbai. He has authored 6 ISBN books in physical and analytical chemistry. He has been actively involved in the Indian national and international chemistry and junior science Olympiads. He has served as a head mentor and delegation leader of the Indian teams to the international Olympiads. We, on behalf of ACT family, acknowledge and hand over this citation to Professor Prabhu during the National Convention of Chemistry Teachers NCCT 2020 at valedictory function on December 1, 2020. Thank you. Professor Dolly Sinha, ma'am, please.
Yeah. Dolly Sinha, ma'am, please show it to Dr. Yeah. It will be sent to D.V. Prabhu sir by post later on.
And declare for that. Thank you. And I request all to please give a big hand to Professor Prabhu.
Yeah.
Thank you, ma'am. Thank you, ma'am. Thank you. We shall send him by post.
Thank you, Professor Sinha.
Yes, Amritji, go on.
Thank you, sir. May I now request Professor P.M. Mishra, sir, convener of NCCT 2020, to deliver the vote of thanks. Over to you, sir.
Okay, thank you very much, Amritji. Respected Chairman, Professor Sudha Jain, ex-President ACT, Chief Guest of the ceremony, Professor Nageshwar Rao, sir, Vice Chancellor, IGNOU, Delhi, Guest of Honor, Professor Dolly Sinha, Pro VC, LNMU, Professor D.V. Prabhu, Founder, General Secretary, ACT, learned resource persons from across the globe, and my dear participants, and master of the today's event, Mr. Amritji. I would like to make this opportunity to take on record our hearty thanks for the support and guidance extended to me by our President, Professor Brajesh Pare, and General Secretary D.V. Prabhu sir. I have no words to thank them for giving East Zone this opportunity to organize NCCT and IWR ECR 20. We feel immensely proud to have a galaxy of learned resource persons who have enlightened we all with their expertise in their respective fields of chemistry education and chemical research. I am thankful to Professor Angela, Michigan State University, USA, for inauguration, release of souvenir and marvelous keynote address on the very relevant topic, chemical education, research and chemical expertise, the key to our future. Other deliberations include Ethics in Research and Publishing by Professor S. Chandrasekharan of Indian Institute of Science, Bangalore, Chemistry Education Today for our 2050 World by Professor Peter Mahaffey, Technology-Driven Education in 21st Century by Professor P. Shiv Sarup, Chemistry Evolves, So Should Chemistry Education by Professor Javier Garcia Martinez, A Quest for Relevance in Chemistry Curricula by Dr. Ankush Gupta, HBCSE Mumbai, Advances in Polymer Blends by Dr. Venkat S. Narayan of Texas, USA, Integration of Research in Science Education by Professor Saurabh Pal, IISER Kolkata, Future of Chemistry and Its Impacts on Education by Professor S. Sivaram, Graphite, Graphene and What Next by P. Ramaswamy, Improving Classroom Assessment, very important component of education, Developing Chemistry Teachers Assessment Literacy by Dr. Andrew Chandler Gravatt, Chemistry for Sustainable Development by Professor Tom Welton of London, Chemistry Teaching for Enhancing Competency of Coming Generation by Dr. Biswajit Saha, Director CBSE. I wish to congratulate our ACT award winners of this year. I am also thankful to Chief Guest of Inaugural Ceremony, Professor K. Subramaniam, Director, Homi Bhabha Center of Science Education, and Guest of Honor, Professor S.P. Singh, Vice Chancellor, NLMU, for their blessings and release of ACT commemorative volume of 20 years of activity. My sincere thanks are to Chief Guest of Valedictory Function, Professor Nageshwar Rao, Vice Chancellor, Indira Gandhi National Open University, and Guest of Honor, Professor Dolly Sinha, Pro VC LNMU Darbhanga, for sparing some valuable time from their busiest schedule to participate in this program. I must mention my deep sense of appreciation to our ex-presidents, Professor S.D. Shamant, Professor Sudha Jain, Professor D.C. Deka, Vice Chancellor, Madhavdev University, and Vice President, Southern Zone, Professor Helen Kavita, for accepting my request to chair the session on very short notice. I am also very grateful to Dr. Amar Srivastav, Professor Shraddha Sinha, Dr. Sudesh Ghodirao, Dr. Umesh Chandra Jain, Dr. Manan K. Murthy. They deserve a special thanks for evaluating the poster presented by our participants. I am fortunate enough to be backed by a team of motivated and dedicated colleagues in ACT East Zone, Dr. S.P. Singh, Dr. Amrit K. Mitra, Dr. Nayan Kumar Bhattacharya, and Dr. Suresh K. Arya, Dr. Hemant Khanolikar. They all deserve deep sense of appreciation for not only working as master of the session, but also helping in many ways to make this event successful. We also would acknowledge our gratitude to all ACTEC members for always standing behind me with open-handed to help in all ways. We are very much indebted to the main pillars of the WebCon, that is participants, for constantly remain connected, without which the program was meaningless. My thanks are also to my principal, Professor B.N. Jha, for accepting my proposal and encouraging me to go ahead. At last but not least, I am also thankful to Sunny for providing glitch-free platform for conducting the WebCon and also designing very good poster and brochure. I am thankful to all whose name I may be forgotten, who have directly or indirectly contributed for making this mega event a grand success. Friends, there is always some probability of lapses during the organization of any event. I sincerely apologize for all those lapses and difficulties felt by you people during the event. Thank you all, and hoping similar cooperation in all future events of ACT. Thank you all. Thank you all.
Congratulations, Mishra ji, for successful organization of the event.
Sir.
Yeah. We are fortunate to have such a luminaries in this forum now.
Yes, we all are fortunate.
So
now
congratulations,
this
Mishra sir.
program with a national anthem. So we request you all to please stand up at your place.
Please just sir, Mishra sir.
Yes sir.
Mishra sir, आपने वो रिजल्ट नहीं बताया पोस्टर से.
Sorry ma'am, just I'm announcing the result. Just I'm announcing it. Yeah. Last was the results of poster presentation. Award for presentation. The first day, the names are K. Santa, Amit Kumar, and Amrita Chakravarti. We give 3 prizes. And second date is Sunita Singh, Bhivi Durgaveni, and Naveen Kumar. We shall send the certificate and the amount of prize by post to them. And now we shall stand up at our own place. And we are going to
National anthem.
Now I request Amrit ji, with the permission of chair, you may announce.
Thank you, sir. Thank you, all the dignitaries, research scholars, Professor D.V. Prabhu, sir, Professor Shudha Jain, ma'am, Professor Brijesh Pare, sir, and all the other respected ACT members. We can conclude in CCT 2020. Thank you, Professor P.M. Mishra, sir, for all your efforts and encouraging all of us. Thank you, sir. Thank you, madam. Thank you all.
Thank you.
Thank you.
Thank you. Thank you. Thank you, madam.
Congratulations, Mishra sir.
Thank you, ma'am.
Congratulations.
Congratulations, Prabhu sir.
Dr. Amit, you did very well.
Thank you.
The success of ACT,
Thank you.
not Mishra.
Thank you, Samant, sir.
Thank you. Thank you.
Thank you, Samant, sir.